she's right there. Like, we need a co-chair. I don't want to be alone. Do you want the PDF or the
PDF.
PDF? I'll full screen it when we get there.
And this I will be able to see.
Yes, it'll be sitting right here.
Great.
And I'm going to unplug Bennett's laptop instead. So he can earn his.
Okay.
Yep.
Thanks.
You ready for this one?
Yep. Worst case, we can pull up the YouTube link.
Backup.
So.
Get anything?
Ready to go?
I think so.
All right, I'm going to get started. All right, hello everyone. Good morning. Hopefully you're all doing well and had a lot of fun last night. So this morning we're going to an oral session about neuroimaging. So we'll have 5 talks and then we'll have short teaser talks for, I believe, the full papers for today, so today's posters. Our first talk is from sorry. I'm unable to read it. Zijin Gu from Cornell, and she'll be talking about fMRI decoding. So, thank you.
Hello everyone. It's my pleasure to present my work at MIDL this year. And I'm Zijingu, and I'm currently graduating my PhD from Cornell. And today I'm going to talk about decoding natural image stimuli from functional MR data with a surface-based convolutional network. And so visual decoding is actually a research question that gained more and more attention in recent years, and this belongs to computational neuroscience. And the question basically tries to answer how we can reconstruct the seen stimuli from purely human brain responses. And for human study, these responses are usually measured by functional MRI. And understanding such questions help us have a better understanding of the brain representations and help us to develop better brain-machine interfaces and help us with better diagnosis and treatment of neurological and psychiatric disorders, and even lead to better human-computer interactions. So the motivation from this work actually came from the processing of functional MR data. So we browsed a lot of previous literatures and found a common processing approach for previous work is, let's say, given the 3D brain voxels of brain responses to a certain stimuli. And usually people will do is take a region or several combinations of regions of interest lying in the human visual cortex, and then flatten the 3D voxels to any vector before inputting it to any design models. And those models can either be a GAN-based or an encoder-decoder based, or a combination of the two to boost the reconstruction quality. And here are some previous work of their reconstructions, and on the left-hand side are the ground truth images, and on the right-hand side are the different reconstructions from different works by columns. And those reconstructions are actually the state of the art at the time when those papers were published, but you can see that it's very hard to get both the semantic information and the low-level details correctly from brain responses. So yeah, there are problems in this question. So we identified as universal problems because of the noisy nature of functional MR data, making it less reliable. And also, this is kind of an EO-post problem because it's very hard to get in pixel-level correctness, like both semantic information and detailed information from the brain responses. And also, we identified some weaknesses of previous approach that might be improved. So first is the subjectiveness in the ROI definitions and selection, because different subjects might have different number of voxels in the same region. So it may result in variability across individuals of the model architecture design. And the most important thing is that they mostly ignore the spatial topology of the 2D cortical areas that is very well functionally defined. So our idea is why not develop a cortex-based model. So we got inspiration from the parameterized differential operators. So different from conventional convolutional kernels, which can be expressed by the input function cross-correlated with the basis functions. In PDOs, the cross-correlation was replaced by differential operators of varying orders. And these operators are also linear and can capture local features. So yeah, here comes our cortex-based model, which directly operating on the surface cortex. And we call it cortex to image. This model has two submodules. One is called the cortex to semantic, and the other is called cortex to detail. So as the name suggests, cortex to semantic maps the brain responses to semantic features. And here's the detailed visualization of the architecture design of cortex to semantic model. So basically, we have the brain responses on the cortical surface, which we use a very standard FS32K surface that can be shared across all subjects. And we inflate it to an isohedral spherical mesh, which has 32K vertices and 2 channels representing the left and right hemisphere. And this mesh will be passed through several blocks of mesh convolution residual blocks. And finally, we have a linear layer to map the intermediate features to the predictive features. And to get the ground truth, to train the model, we need to get the ground truth semantic features. And we use another pre-trained network called Swing to extract the ground truth semantic features. And to train this model, we just use L2 loss between the predicted and ground truth features. And the cortex to detail model shares a very similar architecture of the cortex to semantic model. So, but a slightly difference lies in the output layer, where we take a variational approach instead of deterministic by predicting the mean and variance and sample the detailed features from that. And as it's very hard to summarize detailed features or like low-level detail like shape, color, orientation from an image, and there's no literature on that. So we cannot train the cortex to detail model as how we train the cortex to semantic model. So instead, we input the semantic features and detail features to pre-train the instance condition again, and let it output the reconstructed image. And we then can train cortex to detail model end to end by using this loss function. So the loss function contains the pixel-wise reconstruction loss and KL divergence loss and also feature space loss. So we train our model and test it on the natural scenes dataset, which is like a publicly available massive large-scale neural imaging dataset. It contains 8 participants, but here we only use 4 participants who completed the whole scan over a year. And there are like 40 MR scans over a year, as you can see in the diagram. And during these scans, each subject will viewed 10,000 distinct color natural scenes from Microsoft COCO database. And a set of 1,000 images were shared across all the subjects. So in our settings, we use 8,500 images and response pairs in our training set. And the validation, we have 500 image response pairs. And for the test, we use the shared set of 1,000 images. So yeah, here are some of our results of the reconstructed images. And I'm going to first show you some well-decoded examples. So on the first row, you're going to see the ground truth images. And the second row is actually the upper bound of the generator, the GAN we used. So these images were reconstructed based on the ground truth semantic features, and they optimize low-level features. So there's no brain responses involved in this reconstruction. And from the third row to the last row are the reconstructions from 4 different subjects in our data set. And generally, we can see that our cortex to image model can reconstruct the semantic information and the low-level details correctly. So for example, the strips on the zebra body, the orientation of and position of the tree and the plane. And yeah, in the paper, we also show some poorly decoded examples so that we can analyze why our model failed in such cases. So basically, we observed that the model has had a hard time when reconstructing images with multiple objects of different categories. So for example, the image with a giraffe and a girl, one. So some of the reconstructions try to reconstruct it as an animal, and the other 2 try to reconstruct it as a human. So that's because different people are paying attention to different objects when they are in the MR scanner. And also, the second reason might be because of our GAN was pre-trained on ImageNet, and ImageNet is not necessarily a multi-class or multi-object data set, so that might be why our model had a hard time reconstructing multiple objects. And we also did an ablation study when we tried to investigate the effectiveness of the different modules in our model. So on the first row is still the ground truth images, and the second is the reconstruction from the cortex to image model, and the third row is the reconstructions from the cortex to semantic model. So we only try to predict the semantic features, but for the low-level detail features, we just sample it from unit Gaussian. And comparing the second and the third row, we can see that predicting the low-level features is not trivial at all, because without that, you cannot get the position of the bus or the shape of the toilet and wash basin correctly. And the last two rows are the reconstructions from ridge-based method, which is a mimic from previous work. We're just trying to flatten the brain responses and apply a ridge regression on top of that. And obviously, the ridge-based models are perform much worse than the cortex-based models. And we also did quantitative evaluation of our model, where on the top row is the two high-level metrics, where we try to compute the distance between the reconstruction and the ground truth in the feature space. And on the bottom row are two low-level metrics, which is structural similarity and pixel correlation. So generally, we found that our cortex to image model perform the best among all the models. And yeah, as a summary, the proposed surface-based convolution architecture can achieve superior quality in image reconstructions over current state-of-the-art baseline models. And one takeaway from it is modeling spatial information in functional MR brain responses is very important for visual decoding. And from my perspective, I think it's also important for any task that if you want to extract meaningful information from brain responses. And two future directions can be based on this work is first add eye tracking data to examine the attention effect on the reconstructed images. And we can also explore better generative models as generative AI developed so fast in recent years. And we're using better generative models, we might get better reconstruction quality of the images. And yeah, here's the paper link and code link. Thank you so much, and questions are welcome.
Do we have questions from the audience?
So thank you. This is really impressive work. Maybe to repeat the statement, this is really the best talk of today.
Oh,
No, that's a small joke, but it's really impressive work. Are you aware of the retinotopic mapping?
Yeah.
Yeah.
It's a way to define the brain regions, right?
So if I may revert your research, I think you are able to inform cognitive neuroscience of the working and the functioning of the brain based on your success and failure in classification. So more than that, it tells you about the success of your model, it informs us about the functioning of our brain. So congratulations and thank you.
Okay, so you think if the worst reconstruction quality means impair of the cognitive functions in the brain?
For instance, when it comes to attention, it's possible to track eye motion in the scanner.
Oh, yeah.
And if you were able to see whether someone is looking at the giraffe or the person, you have proof of attention, of us looking at images rather than the success of your model. So, yeah, thank you.
Yeah, that's a good suggestion. Thanks.
Hi, thank you. This was a great talk.
Thanks.
So I was trying to get a clear understanding of what are the priors and the inductive biases of the model.
Okay.
Can you go through them again?
Yeah, let me try to pull the architecture back. So here, no. This one, or?
So you don't assume spatial information. You have a pre-trained generative model right from ImageNet that you then kind of transfer to this.
Yeah,
That's
the scan we use here is pre-trained on ImageNet, and it's called instance condition GAN. So it's conditioned on a feature vector, actually. So that's a feature vector is our semantic features here.
Right. Any other assumptions you have about what the subject is seeing or that kind of stuff?
Sorry, can you?
Any other assumptions you have in the model somewhere about what the subject is seeing, for example?
No, we just reconstruct it purely from the brain responses.
Yeah, so mostly limited to what ImageNet has, right? And
oh yeah, that's true. That's true.
Yeah, so if it's not covered in
the
ImageNet
Yeah.
data
yeah,
set,
yeah,
you're
that's
not going to be able to reconstruct it.
Yes.
Is it fine-tuned, that IC GAN?
No, it's fixed. It's frozen.
It's fixed, so from ImageNet. So,
Yeah.
so you kind of retrieve whatever objects from ImageNet best matched the
It's not
stimulus.
retrieval because you are not searching in the
Gotcha,
database.
Gotcha. You're
but
optimizing the latent? No.
yeah, no, you just try to predict the input to the GAN.
Gotcha.
Yeah, and you try to reconstruct based on the semantic information and the detailed features.
And the sampling is just allowing you to sample multiple
Oh yeah,
reconstructions?
yeah. I forgot to mention. Why we do that is because we believe it's generally impossible to reconstruct the exact details from just the noisy brain data. So, if we just try to sample some images that center around the ground truth, then that might be a better approach.
Yeah, yeah. Thank you. Thank you so much.
Sure.
We have time for maybe one more.
Thank you for this. Here.
Oh,
Thank
sorry.
you for this very nice talk. Could you go to the losses, please?
Okay.
Because
Here.
oh yeah, there. So you have pixel-wise reconstruction loss, right?
Yes.
Have you tried like also using SSIM and perception loss? And did you see if that maybe makes some better quality images? But
So, yeah. So SSM is also like based on the pixel. So, it's. Yeah, we think once we have, we didn't try that first, and that's because we think if we have the pixel-wise reconstruction loss, it kind of covers that on the low-level space. So.
But sometimes it makes the quality of the images worse than if you have like some broader.
Yeah, we did
statistics.
try some different losses combinations, but yeah, sometimes it just makes the image in the grayscale and not. Like reconstructing anything meaningful.
Okay,
Yeah.
thank you.
Sure.
Let's thank the speaker one more time.
Is the next speaker ready? All right, the next talk is presented by Dr. Rosenman, Pre-Training Transformers for Fingerprinting to Improve Stress Prediction in fMRI.
Hello, everyone. I'm Goni Rosenman, a PhD candidate in Tel Aviv University. Very happy to be here to present my joint work with the Schools of Neuroscience and Computer Science about fingerprints in fMRI. So let's start with some background. We have the resting state fMRI functional connectivity. It's a measure of synchronization between brain regions. Usually we use a parcellation of a known atlas, and then we compute the Pearson correlation of every pair of regions, and we get the functional connectivity metrics you can see on the right side. And it's shown in many psychological papers to be altered in different cognitive and mental states. Then, relatively new to this, we have the fMRI fingerprint, which is the discovery that those functional connectivity matrices are stable and persistent between individuals and across time. So what that means is if we take a subject, let's call him subject 1, and we compute his functional connectivity in 2 scans, scan 1 and scan 2, and we take another subject and we measure his functional connectivity, then on average, we will see that the pairwise similarity of subject 1 in scan 1 and 2 is more similar than any of them to that of subject 2. And that result is also reproduced in dynamic functional connectivity. So when we compute the resting state functional connectivity in shorter timescales, this can still be witnessed. And it's interesting that it's witnessed in different functional networks in different timescales. So that hints at some kind of individual level information present in the functional connectivity. Now, we wanted to take that and see if we can formulate it as a metric learning task. So instead of using the traditional parcellation and Pearson correlation, we tried to find a nonlinear mapping using a 3D convolutional encoder and a transformer architecture to map the raw 4-dimensional fMRI frames to what we call an effective functional connectivity embeddings. And further, we ask, can this be a pre-training that will enhance accuracy when predicting mental states with large inter-subject variability. So for example, when we talk about stress, that we will talk in the future, so stress is experienced differently between different individuals and not in one specific place in the brain. So maybe fingerprinting can help with that. So that leads to our motivation. This task of fingerprinting does not require labels. We can do it with any resting state fMRI dataset, and that will help us to get a unique representation that contains individual level information. Stress, as we all know, is a big problem, and it's growing every day at a time. And generally, trying to understand where stress originates in the brain at the individual level is a crucial step towards data-driven psychiatry, which is something I consider very important. So now we can talk about the data. So we have resting state fMRI scans. They are pre-processed, denoised. We can see them as volumetric video, and we normalize them by the voxel. So that means you can see on the left side, you can see the fMRI slice before normalization, and you can see that the different scale of intensity reveals still some structure of the brain. And we wanted our model to be indifferent to that, because with this information, the fingerprinting is rather easy. So we normalize each voxel to have 0 mean and unit variance throughout the entire scan. And then finally, we take a chunk of that of 30 time frames, and that's our input, what you can see on the right side. And now for the metric fMRI training pipeline. So it consists of 3 phases of training. They were all crucial for convergence, as we verified with an ablation study. First is rather straightforward, autoencoder reconstruction. We take the voxel normalized fMRI volumes, we encode them with a 3D convolutional encoder to a bottleneck layer, and then we decode and optimize with L1 and perceptual loss to maintain the spatial information and reduce blurriness. Then we discard the decoder and we load the weights of the encoder and stack a transformer. We have a data loader that loads 3 sequences of volumes. 2, the positive and the anchor, they belong to one subject. We call him subject 1 again. And the negative belongs to a randomly sampled subject that is from the same set, if it's the train set, for example. And then we batch them all together and propagate through the encoder, resulting in a series of vectors for each time frame. And we concatenate a CLS token that is randomly initialized. Then we propagate them through the transformer, where they undergo self-attention. Potentially, spatiotemporal information is absorbed to the CLS token, which is extracted, and that is our effective functional connectivity embedding. Finally, we optimize a triplet loss, maximizing the cosine similarity between the anchor and the positive, and minimizing between the anchor and the negative. This way, we effectively formulated the fingerprinting concept as a learning function. Then we load the encoder and the transformer and stack on top a classification head, and we train for cross-entropy. So basically, how did we get the stressful and the non-stressful scans? So our subjects participated in a cognitive motor task, basically playing a joystick game, and they did it 2 times. One time, they simply played the game, and then they went into the resting state session. In the second time, the instructor, without their knowledge, was a trained actor, and he induced emotional stress in them by criticizing them, letting them feel like they failed the task, and so on. And this was also verified with skin conductance that they were really stressed because of that. And that's how we got our labels. So now we can move to some results. So first, for the fingerprinting, we formulated it as a binary classification task. Given 2 scans, do they belong to the same subject or not? Our baselines are mostly seed-based, so they use the parcellation and the atlas. And also we use TFF, which is a work from our group, previous work, that also uses transformers, but not the same self-supervised approach. And we can see that while the rest of the models are having a really hard time with this specific data set, our model is surpassing them by a large margin with 83% balanced accuracy. And we associate this dramatic improvement to the variability in the triplet loss. So there are more each batch contains more variability than in the binary case. Now we can move to the stress prediction. So again, it's a binary classification problem. We have a small data set of 50 subjects, and we compensated for that with a 5-fold cross-validation. And we can see that, again, our model with almost 79% balanced accuracy, while the rest are behind. And we associate this with the triplet loss, with the unique fingerprint that represents each subject in a different way. And this way, stress, which is experienced differently between individuals, is better captured. Now we can move to some validation, or we can say interpretability of our model. So we use the method that uses saliency maps. So we track gradients back to the input space, and then we took the correlation between the gradients. And we can say in simple words that we try to find regions in the brain that contributed to the model's decision at the same time. And this way, for each sample that we input to the model, we get what you see on the bottom right, which is, we call it a decision explanation graph. And then we try to group together decision explanation graphs according to some condition. So in this example, we took the subgroup of patients that actually improved their performance in the presence of stress compared to those whose performance impaired. And we can see two interesting things that arise. So first, luckily, both groups are showing sensitivity in limbic regions, which are responsible for mood regulation. But more interestingly, we see that they have statistically significant differences in basal ganglia regions that are known to be related to motor learning and reward planning. So what that means is that we have two groups, and we know that they have different coping mechanisms, because one group actually improved due to stress and one didn't. And we see that our model was able to look at different regions to predict stress in a way that was correlated with this behavior pattern. And that's exactly what we were hoping to find, since we don't want to find just one place in the brain where stress arises. We want to have a more sensitive approach and more individual approach. So we can actually summarize. We found a novel self-supervised objective that is unique for fMRI. We use triplet loss to encode effective functional connectivity embeddings and to find individual level information. And then we use this to map stress in the brain. We see that without the pre-training, the stress could not be predicted. And we did it with a very small data set. And also, we saw that there was a very specific division between two groups that had also correlation with their behavior. So that's it for now. What we would like to do in the future is try to predict the fingerprinting on larger data sets and to explore the latent space arising in the effective functional connectivity embeddings. That's it. Any questions, please?
Great talk. Are there any questions? I was curious, in addition to training on the full 3D volumes, have you also experimented with training on ROI-based or parcellated data?
So one of our baselines is the functional connectivity version, the ROI-based. And yeah, there is a great advantage to using the ROI that is computational effort. But what we want to find is the individual level information. And with our approach, we can pinpoint the exact location. And we show that this actually contributes to different divisions, to different populations. And in the future, we could actually use that to find subtypings of certain disease, I hope.
Great. If there are no more questions, then maybe we'll move on to the next talk. Thank you so much. Let's thank the speaker.
our next speaker will be Axel Aladi, speaking about E3 across SO3 equivariant networks for spherical deconvolution in diffusion.
Okay, let's go. So hi, I'm Axel and a PhD candidate at NYU, and I will speak about equivariance in neural network and diffusion MRI. So the goal of our paper is to develop a convolution on spatiospherical signal, such as a diffusion MRI, and with the objective of improving the estimation of local white matter tissue orientation. So first, what is a diffusion MRI? Diffusion MRI quantifies voxel-wise water diffusivity along a set of gradient directions. So for each gradient direction, we get one MRI image. And to be more specific, at the voxel level, diffusion MRI signal can be represented as a spherical function. And now different models try to relate the underlying fiber directions with the diffusion signal. And in this talk, we will rely on a model called a constrained spherical deconvolution, which assumes the diffusion signal to be decomposed as a convolution of a fiber orientation distribution function, or FODF, which characterizes the underlying tissue directions, and a response function, which is supposed to be known. And we can recover the FODF through solving an inverse problem by minimizing a reconstruction loss between the diffusion signal and the convolution of the FODF and the response function. And moreover, to respect the physical property of our distribution function, we also use two regularizers on the FODF. The first one is the non-negativity, and the second is the sparsity loss. So now, most recent work try to use deep learning to estimate nonlinear FODF. And this network are either trained supervisedly using the output of the CSD model, or unsupervisedly using a similar framework as the CSD model. And since we are working with spherical signal, the latest work tried to leverage the spherical convolution as a basis layer. And the spherical convolution has one really important inductive bias on the spherical grid. This bias is called SO3 equivariance, or rotation equivariance, where SO3 is the set of all 3D rotation. And SO3 equivariance simply means that if we rotate the layer input, this translates into the rotation of the layer output. Yeah. So as you may have noticed, we have only spoken about recovering the FODF on a single voxel. Indeed, most of the previous method deconvolves the diffusion signal on a voxel-wise manner, disregarding useful spatial information. And we argue that neighborhood voxels are likely to yield similar FODF. And thus, if we include spatial information into our model, this should lead to a better estimation of the global orientation. So our motivation is to incorporate spatial information into spherical neural networks. And for this aim, we try to develop a convolution on spatiospherical function. And our main contribution is to make sure that this convolution has the right inductive bias on the spatial and spherical domain. This bias, so we constrain our convolution to be equivariant to any independent transformation on the voxel and grid level. So this transformation can be either the voxel rise rotation, which leads to the SO3 voxel equivariance, and the grid rise rotation, translation, and symmetry. And this leads to the E3 grid equivariance. So how does it work? So first, the input of our convolution is a grid of spherical signal. And because spherical operation has been efficiently implemented using spherical graph, we actually use as input a grid of spherical graph. So the first step of the convolution is the voxel-wise Laplacian graph filtering, where this filtering can be seen as an isotropic graph convolution. Then the second step is a vertex-wise isotropic 3D convolution on each 3D map arising from each spherical graph vertex. And finally, to get the output of our convolution, we simply sum across the spatial and spherical input features. So we have two main advantages with our formulation. The first one is that the learnable parameters alpha k are shared across the spherical and spatial features. And moreover, by using an equivariant neural network, we have better generalization power to unseen transformation. So now that we have our spatial spherical convolution, we're ready to use it in a model to better estimate fiber orientations. And we leverage the two previous work, which are voxel-wise. The first is equivariant spherical deconvolution, which is a spherical CNN-based deep learning version of the constraint spherical deconvolution. And it's important to notice that this two model doesn't take into account any spatial information. So the basic block of our model is a unit, but instead of using a usual convolution layer, we use our E3 SO3 convolution. And because the pointwise ReLU nonlinearity, bunch norm, and max pooling are equivariant, we can use them as they are. And here, it's really important to notice that the discretization of the spherical and spatial domain introduce equivariance error. So for the other part of the network, the first one is an interpolation of the raw diffusion MRI signal into our spherical graph. And the output of our unit are the predicted FODF. And we train our network unsupervisedly using the reconstruction between the raw diffusion MRI signal and the convolution of the predicted FODF and the response function. We also use the two regularizers on the FODF, namely the non-negativity loss and the sparsity loss. Okay, so now we are ready to study the impact of using spatial information into an FODF estimator. For this, we compare our model against the two previously mentioned models, the constraint spherical deconvolution and the equivariant spherical deconvolution, which are both voxel-wise and doesn't take into account spatial information again. And also, so FODF validation is a bit tricky because we don't have actual access to ground truth tissue directions. So we have to rely on synthetic dataset or downstream application of FODF. So the first synthetic dataset we use is from the DISCO challenge, where we know the local fiber orientation. So we can compare our estimation of FODF against the ground truth. And by using spatial information, we can see that we can decrease the number of spurious and missing fibers, which leads to a more accurate estimation of the number of fiber per voxel. And we can also notice a higher precision in the fiber localization. So now the second dataset we use, which is also synthetic, is from the tractometer challenge. And with this one, we can study the impact on a more global scale by means of fiber pathway recovery. On this dataset, we know the global fiber bundle architecture. And by using spatial information, again, we can see a decrease in the number of spurious fiber streamlines, and also an increase in the overlap between estimated and ground truth bundles. But this comes with a drawback of a higher number of overreaching streamlines. And finally, we can also study the applicability of our model on in vivo human brain. As I said earlier, we don't have access to any local orientation, fiber orientation, or fiber bundles in a human brain. So we use a side result of our FODF estimation, which is a tissue partial volume estimation. And from a T1 or T2 image, we can get a ground truth probabilistic tissue segmentation, and we can compare our estimated tissue segmentation by using a KL divergence. And we can see that, again, by using spatial information, we can give more accurate and coherent tissue segmentation map. So in summary, we develop an E3 SO3 equivalent convolution, which we use in a unit network for the application to white matter fiber orientation estimation that takes into account spatial information. This led to a better anatomical recovery in terms of tissue orientation and partial volume estimation. However, our work has two main weaknesses. The first one, the core validation is performed on synthetic datasets. So we need some extension to study the FODF estimation on in vivo datasets or in clinical setting. And I think, like, as a lot of us here, this network is really slow and is highly memory intensive, so which limit our capability to use large input patch size or larger datasets. And finally, I would like to thank my co-author, Guido Gehrig and Neil Dale. And I invite you to read our paper where there is more baseline, more experiment, and more results. And if you have any question, you can come see me at the poster session T07 here. Thank you.
Thank you. Do we have any questions? Maybe I can start out. So thank you for an excellent talk. I had a question about the pooling layers of your UNet. So the convolutions you've carefully constructed to be equivariant, but how did you ensure that the pooling layers themselves are also equivariant?
Yes. So the pooling is actually decomposed into two sub-pooling. Yes, there is a graph. So one on the spherical domain, where we use a spherical graph with a hierarchical structure that allows us to minimize the impacts of the equivalence error introduced by the max pooling on the spherical level. And for the spatial grid, we also use the max pooling, which is, in theory, equivariant, but because of the discretization of the grid here, it's also introduced some error. And but in the paper, we have like some experiments about the equivalence error of a random layer that we developed, and we can see that this equivalence is still low, even with this non-equivalence error. Yeah.
Oh, thank you. We have a question from the floor.
Kind of related. Thank you. Amazing talk. Thank you so much. You mentioned that you get an error in the equivariance because you have to discretize. Do you have ideas on how you could fix that in future work, or do you think that's just an inherent problem of working with computers?
So that's an inherent problem. I think it's an inherent problem of working with a computer because we have to discretize. A way maybe to solve this is to go in a spectral domain where well, you have a continuous representation of your signal, but then here everything is even slower and require even more memory. So that's why we are like focusing on a grid and graph because it's just faster.
Great. Thank you.
Thank you.
Thanks.
Hello. Thank you for your talk. I have a so I'm still about to understand this, so I'm not sure if what I now ask makes sense. But how does your approach for your deconvolution approach or relate to like classical deconvolution or analytical variational deconvolution approaches? Would something like that be also feasible for that problem setting?
So if you need to do a deconvolution on the spheres, I think like in weather, with weather data, you need some deconvolution. You can use this kind of thing. But like, so for a single sphere, for a deconvolution of a single sphere, this problem has already been solved with a spherical convolution and the S2CNN network. And here we just say that, hey, now you can also, if you have, I don't know, multiple planets and you want to study the relation of the weather between these planets, you can also deconvolve on all these planets. I don't know if that makes sense, but.
Yeah, no, I mean, so I come from, my simple image in mind is you have an image and you want to deconvolve it.
Yeah.
And the variational approach that I understand is you formulate it as a convex minimization problem. You do your least square minimization with non-negativity or whatever you want.
Yeah.
And is this a baseline for what you have here, or does it not work?
Yeah,
yet?
it's a baseline. So that's the constraint spherical deconvolution model, which is the baseline, which is like a usual linear optimization of the inverse problem of the deconvolution.
And basically, your approach improves that by a lot. I assume.
Exactly.
Okay.
So there are like other models who say, hey, maybe you can use deep learning instead of optimization-based method. And here we say, hey, maybe we can also improve this deep learning method with a more inductive bias of your data.
Perfect. Yeah. Thanks a lot, and really cool talk.
Thank you.
Okay, we have time for one more.
I have one quick question. So one of the challenge in DTI is like, we have two fiber crossing each other. So I'm just, can you comment a little bit on whether your spatial convolution will help to solve this issue or will affect this problem?
Yes. Yes, so how to, so we do study, so when I show the result of a better fiber localization, we speak about this problem of if you have multiple crossing fibers in your voxel, you want to be able to detect the 3 fibers, and even if they are close to each other. And so if you have a better localization of your fiber, you can detect, you can separate 2 close fibers on your diffusion signal. So by increasing the localization, we also increase our sensitivity to multi-crossing fibers which are close to each other. But this is mainly solved thanks also to the sparsity loss, which gives us a sparser FODF. And yeah, I hope that's answer your question. I don't know where you are. Okay.
Let's thank the speaker again.
Thank you.
All right, the next talk is Amortizing Normalized Flows for Transcranial Ultrasound with Uncertainty Quantification, presented by Rafael Orozco.
Hold on, let's.
I think I prefer the PowerPoint.
Okay. It's already presenting, but not on our local, so 1 second.
If it's easier, I can do the PDF.
Yeah, we're already on the screen up here, but you need to be able to see it here, so.
Oh, just twist my neck.
That's bad for your bones.
No, it's fine.
Okay, let's try it.
Sounds like it's such a slide.
Yeah. No.
Don't worry about it. I can just.
Okay. Are you okay with it?
Yes, yes,
Okay.
absolutely. So my name is Rafael. It's going to be a pleasure to present some of the work I've been doing. I'm going to warn about some other technical difficulties that I had when exporting this from Keynote to PowerPoint, which was completely my fault. Daniel's amazing. It's all me. I just had too much fun last night, and I didn't check it before I uploaded it. But hopefully, we can work through it, and I can clearly explain this work I've been doing. And my goal, I'll have 2 goals. I'm going to present what is a quite novel image modality. It's actually only 3 years old, so I actually think this will be a big part of the discussion. I'll welcome questions just on the modality, not even my approach to how I solve it. It's going to be based on waves. It's going to be ultrasound waves. And then my next goal will be to very clearly show that my method will need to combine deep learning with physics. So just deep learning will not be enough. We'll need to combine it with the domain physics that we know of the problem. So I'll present the modality first. This is a wave-based medical imaging modality. And it's based on ultrasound transducers. So these are the same ultrasound transducers that you would use for B-mode ultrasound imaging. And what you would do is you basically form a helmet. That helmet has 1,024 of these transducers. You would wear it. You'd have some transducers emitting waves, while the rest of the transducers are receiving these waves. And I put a simulation of what's actually happening when these waves go through. And you can see that the waves are very complicated. It's bouncing. It's bouncing on acoustic contrast, on contrast in the speed of sound that is traveling, and it's being received by all these transducers all around, and the goal is to make images from this data. Literally, the data you're receiving is the full waveform of pressure that's measured at these transducers. So in the middle, I put what a single transducer would be measuring, which is the waveform over time, and if we were to place all these transducers on columns, then we would get an image like what's on the right, which is the full waveform. We can see it's very complicated. It's more information than what you get from B-mode, but you can do more with it. And the goal would be to get from that very complicated waveform to a very high-resolution image of the tissue in the brain. In this case, it's the quantity of interest is the speed of sound. So by the end of the talk, if I can do something like this, then I'll consider it a success, but that can currently be done. The first paper on this modality showed that this can be done 3 years ago. It was published in Nature, but it was extremely computationally intensive. They had a very nice cluster, and it still took them more than a day to make a single image, which really does not make this a clinically viable option. So my goal would be to make this faster, to either have on par quality or better quality, and I want to introduce a probabilistic approach to solving this problem because it is ill-posed. So it's a helmet, you're not receiving all of the waves. Some of the waves that are bouncing actually go below that are not received by the transducer helmet. So you're not getting all the data, and it's noisy, therefore it's gonna be ill-posed. So any method which gives a single point estimate that's trying to estimate this image is going to be inherently not as informative as we need it. What we're actually after is gonna be the posterior, the Bayesian posterior. So P of X, where X here is the image, we're conditioning on our data Y. We actually want to sample many images that could match that observation Y. The reason why we want to do this is because we're going to get also very high quality point estimates, such as estimates that are mathematically guaranteed to minimize the MSE, and also importantly, we're going to be able to get uncertainties, which I think is very important for an ill-posed problem in a medical imaging setting where we need to be very risk averse. And here are just some previous examples that I've worked on other image modalities, where I've shown that the uncertainties that we provide correlate very highly with the error that your model is making, which is going to be very useful if you can communicate to a practitioner, do not trust this part of the image, which is either, the practitioner is either going to respond, that's okay, we didn't need that part of the image to be well resolved, or that is not okay, you need to receive more data, you need to go do something and get me a better image. And we can see that the uncertainty, here is the third column, UQ, is correlating very highly with the error. But these are simpler problems. These are linear photoacoustic imaging and computed tomography. Our current problem is nonlinear, so we're actually going to have to add some more machinery to get this to work. The way we are going to attempt to sample from the posterior is going to be a little bit non-traditional. Traditionally, you'd have to form the Bayesian posterior by actually convolving the prior with the data likelihood. Here, the prior is the prior on brains, which isn't exactly an object we understand. We can't just assign a Gaussian prior to that. And the likelihood is related to the wave physics, which is very expensive. And if we go down that traditional route, we end up where we started, where we have to spend a whole day just to form an image. So we're going to go down the variational inference route, which will take a family of known, simple, easy distributions and sort of fit that to the data such that you can sample. And in this work, we're going to go through that by doing generative deep learning. And I think here it's going to be an interesting topic. So I think normalizing flows are kind of like the middle child right now. GANs had a very good moment, and right now it's diffusion. I think normalizing flows kind of got lost in all of that, but I think it'll be very fun to explain it, and I think it's very cool and it offers some very good pros. But very simply, normalizing flows, they basically normalize your distribution. They learn a mapping from your complicated distribution. Here I've described it with this multimodal distribution to a simple one, and the simplest of all is the Gaussian normal distribution. And importantly, that distribution that you learn has to be invertible. You need to be able to go, you need to be able to take any of your layers, here I'm describing it with f of theta, and you need to have a known analytical inverse. And that's sort of an example of what would look like, going from a complicated two-crescent moon distribution to the Gaussian. But importantly, you need to be able to reverse that such that you can, after training, go from your simple distribution to your complicated distribution. Here, I'm demonstrating it with the complicated distribution of faces, where after training, you can sample Gaussian noise, which is very easy to do. But because you have an inverse, you've learned to slowly morph from noise to a sample from your complicated distribution. And it's a very simple training objective. And I emphasize simple because GANs will have a competitive loss, which will be hard to fine tune. And diffusion will have a very difficult sampling phase. But here, this is a very simple objective, which all you need is samples from your target distribution. And you can train this very simply. And there are other reasons why this is good. In fact, I encourage questions like why do I actually think this is better, or why it has advantages compared to GANs or diffusion. But that will just sample from a marginal distribution. We're actually trying to get the posterior, which is a conditional distribution. So there, we just need to go to a very simple novelty on normalizing flows, which is conditional normalizing flows, which end up being very simple as well. You just need to condition your networks on the data that you're trying to condition on. So here we just condition on Y, which is going to be that acoustic observation. We actually have the machinery that we would need to perform Bayesian sampling on an inverse problem where you have these examples X, Y, but there's going to be some challenges for our particular problem. So as I explained, we're trying to go from that complicated waveform to those very pretty brain images. But if you're to throw this problem at a conditional normalizing flow, because it's nonlinear and because it's so high dimensional, it's actually going to fail. So if you train with a lot of these pairs and then on testing, you take your trained network, you put in your data, then you're going to get samples that are not coherent. It's not learning to generalize to the test data set, which is expected. We've actually observed this on a lot of other applications. My lab actually does seismic imaging, and we've observed this phenomena before. So that's one of my conclusions where I'm saying deep learning by itself will not be enough. For that, we propose a solution where we're going to try to incorporate the known physics of our problem. So there are a lot of ways we're going to do this. Here, I propose that we look at the gradient of the data misfit, which is defined as a data residual, where here F represents the physics of the problem, and you're actually comparing at a starting guess, x0, like your best guess of what you have of the brain, and you compare the wave simulation at that guess with what you observed, y, and you try to minimize that data misfit, and you, someone was mentioning about a variational approach, you just calculate the gradient with respect to that. And the gradient in this case, just to demonstrate, looks something like this. You get some artifacts related to all the transducers that are all around, but really what this represents is the update that you need to get from x0 to a model of the brain which would best match your data. So very simply, and there's a lot of interesting math that goes behind this, you can now learn another conditional distribution where you're learning to go from these gradients to your images. And when you train on these samples, you get closer. Now your process looks a little bit different in testing. You go from your data, now you calculate a gradient, which will involve physics, and we'll talk about that computational demand. And now you get posterior sampling, which is better. We have more coherence. Now we got the skull resolved correctly. And these images will actually stack up, if you compute a mean, to a very good image. But I do not think it's quite there. And the reason is that the quality of the gradient that we're computing depends on the quality of the starting guess. It's a nonlinear problem, so you can imagine that that starting guess is at a very bad point. That gradient will actually be completely uninformative. So here we propose a new novelty, where we're actually going to reuse the previously trained network to create a new starting guess. So we started with just the bone. We're going to train a network such that after we train it, we can sample from the posterior, and we get those samples that aren't good. But if we stack them out and create an average, we get that lower left image, which is better than your previous starting guess. So, and the math says that your next gradient is going to be more informative, and you can just repeat the process. Now train on these new gradients. And it kind of brings an iterative framework where the physics is informing the machine learning. Apologize for the formatting, but here's an important question. Here I'm putting two conditional distributions. Have we changed the posterior? We seem to be learning a new conditional distribution. Previously, we were conditioning on the observation, but now we're conditioning on the data. And just by looking at it, these seem like very different objects. But I'll quickly go over these mathematical sites. We've done work that in linear operators, in linear medical imaging problems, such as computed tomography and photoacoustic imaging, these are exactly the same, but our problem is nonlinear, and here we have to use some more complicated mathematics with regards to information theory. But basically, we arrive at the same conclusion. It depends on the quality of the starting guess if these two posteriors will be the same. With that, I'll just quickly go into the results. So I'd like to make very clear what I need for my method to make this work. I assume that I can sample from a prior. I don't really have an analytical expression for it, but I can sample examples from it. So here they just look like the images of the brains that we're trying to get. And I'd love some discussion on how I got to there. I actually made these images. These are acoustic images from MRI images, kind of an involved process. You need to make an observation, a synthetic observation, by running your physics simulator F.
and then you need to calculate a gradient, which will involve another simulator. You can see it f on x0. And then you just train a conditional normalizing flow on these new pairs, x and your gradient. During testing, you would take some reference point, some starting guess x0. You would use that in tandem with your observation y to create a gradient, and you do this posterior sampling. That as you iterate through those iterations that I was talking about, the posterior sampling slowly gets better and better. So each of these steps has one gradient call, so we don't want to do too many of them. We've actually found that depending on the complexity of the problem, we can get away with around 3 to 5. In this case, we got away with 3. So these are some of the main results. Again, apologize for the formatting, but we have the ground truth image on the right and our method in the middle. And the baseline that we're using is the variational approach, where you just form a data misfit and you just do gradient descent trying to minimize the data. We are much better because our method has examples of the prior X, so we can get there much closer. The SSIM and PSNR metrics are much better. It was a 5 dB and then like 1 SSIM better. But just visually, I think it's very clear. So we're better, and very importantly, we can get there much faster. The x-axis here is what I'm calling compute time, which I've quantified by the number of simulations that you need to make. And a gradient descent approach would take on the order of 100 iterations, whereas each of our iterations of our conditional normalizing flow only takes a single gradient. So we can get there in a factor of 10 faster. And on the y-axis, I'm just plotting the quality of the image. So we can get there much faster than the day that it was taken before. And importantly, as I said, one of the things that we wanted to get to was to get uncertainty. The way we get uncertainty is we just take these posterior samples that are very easy to calculate. They take milliseconds, and we just do image by image variation on these. And we want more than just a pretty image. We need these to be useful to a practitioner. So we're interested in the uncertainty correlating with the error that we are making. So here I'm comparing with the current method for probabilistic imaging that exists, which is a Laplacian approximation. And their uncertainty, because it makes a Laplacian approximation, which assumes that you have a diagonal Gaussian distribution, it cannot capture, I'm looking on the left, it cannot capture long-range correlation, so it's not giving useful, interpretable uncertainty quantification, which in the end is not correlating with the error they're making. Whereas our uncertainty, because the uncertainty is being learned by deep learning, it can learn all these relationships. It really aligns with the structures that we're making error in, and it's correlating much better with the error that we are making. To conclude, if we combine deep learning with the physics, which incurs an extra cost, but because we did it kind of efficiently, it's still very fast. We can get this very fast image, we can get it very accurate, it's on par with the traditional ones or better, and now it's uncertainty aware. So I think this does bring the technology 3 years old, I don't know, maybe in 10 years it will be used in hospitals. I think we're bringing it to clinical viability. And for the future steps, we actually want to use this uncertainty for a little bit more than just correlation with error. We can actually use it to decide where to place transducers or where to actually measure more experiments. And I'd like to emphasize this last one. We want to extend it to 3D, but we do not have the data sets. And I would welcome input on what data sets we could use. We want 3D data sets of brains, and we need to be very high resolution. I mentioned that the data set I used was from fast MRI, but it just wasn't quite the resolution that we needed on the slice direction. Thank you so much for your attention. I'd welcome questions.
And thank you for being flexible with our
thank
technical
you.
difficulties and risking neck injury.
Yeah.
Great question.
Hey.
So thank you for an excellent talk. I really wish for future students for you to be that teacher, actually. So.
Wow, thanks. That's very kind.
So can you tell a bit more
Sure.
about the relation between your ultrasound modality and, say, CT or MR? Because I would say that sparse CT acquisition is also ill-posed. So
yes.
Where do the two deviate from one another?
They do not deviate a lot. In fact, we first did it with computed tomography just to get an idea. I'll just pull up the computed tomography results so we can be staring at it. It was not on brains, but it's useful. I would say that the main difference is that our physics is going to be nonlinear in this case, whereas it's going to be a linear in CT. But in CT, you get different types of noise, and that actually presents its own difficulties. Yeah. So I'm not saying that one is harder or easier than the other. But yeah, it's very interesting there.
So I think other modalities can also learn from your work. And if you're interested, we have some 0.5 mil isotropic MR data. So
I'm there,
maybe we should
yes.
talk.
Yes,
Yeah.
please. I'll
Thank
talk to you afterwards. Thank you.
Hi, thanks for the talk. Maybe a stupid question.
Yeah.
Could you use these simulations that you have then intermediate steps and have it as a signal for like one step supervised learning from the input data to the direct data?
Are you talking about the waveforms?
Yes.
I love that idea. You get to use very interesting architectures if you do that because it has a time dependence. It's a little bit hard because these waveforms are very long in time. They're finely sampled, so it's going to be very memory intensive. But I think it offers some very cool ideas on the different inductive biases that you'd get by network that now depends on time. I love that idea. I haven't explored it, so I might talk to you about it, yeah. Yeah, it's very cool. Thank you.
Okay, great. Thank you so much. Oh, any other questions?
Poster 1, right there. Thank you.
We seem to have broken our mirroring, so hold with us for 1 second. All right, thank you. So our next speaker is Nalini Singh, who will be speaking about data consistency in deep rigid motion, assumably in the frequency domain. So.
Okay, thanks Daniel for that introduction. So MRI is a really popular imaging modality. It's non-invasive and it's non-ionizing, and it gives you really nice images that look like this. Unfortunately, in about 16% of cases, you end up with motion artifacts which really severely distort the quality of the image that you get. And also this comes at a significant computational and time cost. So this talk is about how to computationally retrospectively correct these motion artifacts without needing to reacquire the scan and without needing to change the clinical workflow. In order to understand how we're going to do this, we need to think a little bit about the physics of MRI. So in particular, MRI is acquired in Fourier space. So this is the equation which governs which measurements you get from the scanner. X is the image that we're trying to image, and we acquire data from a bunch of different coils. And if you're not familiar with this, you can think of each of these coils as sort of spatially emphasizing different parts of the image. After that, you do a Fourier transform on the resulting image, and up to some noise, this defines the data that you're going to get right off of the scanner. So in order to acquire this data, you basically need to do a raster scan across all of those points in K-space. And this is pretty slow and makes you even more susceptible to motion. So in practice, what people do is they undersample their data. And so now we've introduced this undersampling operator U, and all this is basically a selector matrix. So this just specifies which points we do or don't acquire. And so you can see now we have to acquire much fewer points, but this comes at a cost. So the image is now pretty significantly artifacted. And even beyond this, even if you keep undersampling, you can still have residual motion artifacts in the image. So now you see that this image looks even worse. And if we look at the forward imaging operator, instead of just a general undersampling operator, now we've split it into an undersampling operator which is specific to a bunch of different shots. You can think of these as just sort of segments of K-space that are acquired together. And at each of these segments of K-space, the object is undergoing a rotation and a translation. So we'll deal with rigid motion in this talk. I want to emphasize that the challenge here is really in this rotation and translation. So compared to a lot of other inverse problems, this one is really challenging because this forward operator is variable and it's unknown. So if you have a data set of a bunch of different images, these motion parameters are probably different from image to image within that data set. And also, in general, at test time, you don't know what the motion parameters are. So we don't even really know how to write down this forward operator for a particular image. So our goal then is to estimate the underlying image x from these corrupted measurements y. And here I've just consolidated that forward model into the capital A there. If we assume that epsilon is complex valued Gaussian noise, we can write down the posterior probability of any given image given the measurements that we acquired off the scanner. And if we ignore the constant term, there's basically two terms of interest here. So one of them is a prior. This just says how likely is this image in general. And the other one is a data consistency loss. And so what this says is if you start off with your image x, you pass it through a simulator of your forward model, how similar is that result with the measurements that you got off of the scanner? And this loss is going to play a pretty key role in some of the methods that we'll discuss next. So there's been a lot of previous work on problems of this form. I'm not going to go into all of the classical approaches for doing this, but most of them typically set up an objective function like the one that we saw on the previous slide, and then optimize that. These are typically pretty slow, so there's been a lot of recent interest in using deep learning to accelerate those solutions, especially for the undersampled reconstruction case. And empirically, we've also seen that these often just give better results than the classical solutions. So there's basically two classes of methods here. The first class of methods doesn't really take into account the physics at all. We saw some discussion of this in the previous talk. So here you have, say, a convolutional neural net. You feed in your corrupted data as input, and you get corrected data as output. There's no notion of the physics in the architecture of the network or the training strategy. A second class of methods uses data consistency-based updates, which require knowledge of that forward operator A. So here's sort of a prototypical setup for one of these networks. You start off with your corrupted data. You feed it through some convolutional layers, which do some updates, which implicitly are modeling the prior that we're interested in. And then you do sort of a classical optimization step. And you just repeat this process a couple of times until you get a nice reconstruction. And I want to emphasize that in order to do this optimization step, you need to know exactly how to write down that forward model A, which is something that we can't do in this motion corrupted case. So with that in mind, there have been a couple of deep learning approaches developed specifically for the motion case. And most of these involve searching over both the unknown motion parameters and the image itself. So one recent method uses a neural network basically to initialize an image estimate, and then it does classical steps where you update the model, the estimated motion parameters and the estimated image. Another recent approach just uses the network basically to provide an estimate that models the prior, and then at test time, you run an inference time optimization over both the image and the motion parameters. So what these methods have in common is that you have to do a search over both the image and the motion parameters. And this is really a computationally intensive thing. So this problem is very non-convex. It has a lot of local minima. And typically, finding solutions to it takes a really long time, or you just don't get there at all. So in this talk, what I'm going to propose is a strategy which will dramatically reduce the complexity of this optimization. Instead of searching over both the image and the motion parameters, we're just going to have to search over the motion parameters m. And so the key idea here is really, really simple. All you need to do is set up your network to be a function of both the corrupted case-based data and the motion parameters themselves. So here we have our network F. The inputs are the motion corrupted case-based data y and the motion parameters m. And then the output of the network is some motion corrected case-based data, which you can use to reconstruct your image. In practice, we implement this network F with a hypernetwork. So the motion parameters m are the inputs to one network H, and the output of that network is the weights of another network G, and G is the network that actually does the reconstruction. So you can think of this setup as producing a motion parameter-specific reconstruction network, and this kind of mirrors the dependence of the forward model on the motion parameters themselves. If you didn't catch all the details of that, that's fine. The key thing to take away from this slide is that the network is, again, a function of both the motion corrupted case-based data and the motion parameters. So we train this sort of the standard way you would train any network. We use an SSIM loss on the reconstructed image, and we use that to find the best value of the network parameters theta that minimize that SSIM loss. And so now, at inference time, when you have a new example, you don't know what the motion parameters are to use as input to this network. And so at inference time, what we're going to do is run another optimization, and this time we will optimize the motion parameter inputs themselves. And so at this point, you might be wondering, how can you run this optimization for this new test example? We don't have any label that we can use. And so the answer is that we'll use this unsupervised data consistency loss. This is motivated by the probabilistic image formation model, which I described earlier in the talk. And it doesn't require any access to a label. You can do it with just the measurements that you started off with. So the way this process works is you start off with some initialization for the motion parameters m. You pass that through the network to get an initial reconstruction. And then you feed that reconstruction through the forward model and compare the result with the motion corrupted measurements that you started off with. This is the data consistency loss that we're interested in, and this whole thing is differentiable. So now you can backpropagate and update your estimates of the motion parameters m, and keep doing this iteratively until you've minimized the data consistency loss. So what are the benefits of this approach? First, as I mentioned earlier, we now have a dramatically more simple search that we have to perform. So instead of optimizing over both the image and the motion parameters, now we just need to optimize over the motion parameters, and we kind of get the image for free as an output of the neural network. Second, because our method produces explicit estimates of the motion parameters, we have the ability to reject poor reconstructions. So 2 reasons that you might get poor reconstructions. One is if you have the correct motion parameters, but your network just produces a poor output. Another thing is that you might just end up on a bad estimate of the motion parameters. In either case, this data consistency loss is going to be high, and we can monitor that and know that we should reject that poor reconstruction. Okay, so we do these experiments on a data set of 2D FLAIR FSE brain MRIs. If you're interested, you can see the acquisition parameters on the slide. And as I mentioned, we simulate our data. So we use a data set of several hundred training, validation, and test slices. And we simulate these artifacts via the forward model, which I showed earlier. In particular, we have a 6-shot acquisition. We randomly select one of those shots at which motion occurs. And then we simulate rigid in-plane translations and rotations up to relatively large values in the motion correction context. This is how the simulation works. We start off with motion-free data, and we apply our sampled motion to get a moved image. We estimate the coil sensitivity maps and use that to simulate the k-space that would have been acquired in the 2 different positions. And then we mix the appropriate lines of k-space data to simulate what you would have gotten off of the scanner if the subject moved from the blue position to the red position over the course of the acquisition. We also have a bit more of a realistic data set, so this is just one slice. And here what we've done is we had the same subject in the scanner in 2 different positions, and we mixed the k-space data from those 2 different acquisitions to simulate what you would have gotten if the subject moved from the first to the second over the course of the acquisition. Okay, so we'll compare to a couple of different baselines. The first group of them I'll describe as motion naive, and this means that these baselines don't do any modeling of the motion parameters at all. So the first of these is called ARC or GRAPPA. You may be familiar with this. It's just a classical reconstruction strategy. It doesn't do any correction for motion, but it's used pretty commonly in the clinic. The second of these I'll call CONV. This is just a standard convolutional neural net. It doesn't do any modeling of the motion as well. So we also have another class of baselines. I'll describe these as motion aware. These methods assume that you have access to the true motion parameters, which isn't realistic, but we'll use this to get sort of an upper bound on how well we can expect our method to do. So the first of these is a model-based approach. What we do here is we take the k-space data and we apply phase shifts and rotations, which correspond to image space translations and rotations, and then use a non-uniform Fourier transform to do the reconstruction. Our final baseline is basically our setup, but instead of optimizing for the motion parameters, we just use the ground truth motion parameters themselves. Okay, so here's a sample result. This is the ground truth that we're trying to reconstruct. This is the motion corrupted data that we feed as input to the network. These are the results from the motion naive and the motion aware baselines. And then this is the result from our method. So you can see, especially as highlighted by the yellow arrows, our method is able to correct some artifacts that you can't get rid of with the motion naive baselines. And we perform comparably to the motion aware baselines, even though we don't assume access to the true motion parameters. We can also look at this quantitatively. So here I'm plotting SSIM across the data set. Higher is better. And these are the results just for the raw inputs with no processing. Here's the results for the motion naive and the motion aware baselines. And then here's the results for 2 versions of our method, with and without the automatic outlier rejection. And so you can see once again that quantitatively, our method outperforms the motion naive baselines, and we perform comparably to the motion aware baselines, even though we don't require access to the motion parameters. And this isn't just true on average across the data set, it's actually really consistent across individual examples. So here I'm showing histograms for all of the examples in our test set of the improvement that we achieve relative to the 2 motion naive baselines. So basically, to read this graph, you want to be to the right of that dotted line, because if you're to the right of that dotted line, this means you've improved on the baseline. And you can see that in the vast majority of cases, we are to the right of that dotted line, and for most of the cases we're not. Those are also cases that were automatically rejected with our rejection strategy. Finally, we can also look at how well we do at estimating the motion parameters. So here I'm plotting the error in the rotations and the translations estimated by our method. And you can see in the vast majority of cases, we get basically 0 error in estimating those parameters for these first 4 shots. For most of the cases where we don't do well, those are once again rejected by our automatic rejection strategy. We can also make the same graph for the last 2 shots of our acquisition. And so our acquisition has this sort of special characteristic. The first 4 shots have a lot more signal energy than the last 2. So here we're doing worse at estimating the motion parameters. And this is kind of expected. These shots participate much less in the data consistency optimization that we're doing, so we don't do as well as estimating the motion parameters. But at the same time, these shots participate less in forming the quality of the final image, so we can kind of get away with this. Finally, here's the result on our realistic data set. So here we have the ground truth image, the motion corrupted image. Here's the results of the two motion naive baselines, because we don't have access to the true motion parameters here. And then here's the result of our method. And you can see that unlike the baselines, we produce really sharp reconstructions that preserve sort of all of the details in the image. So I'd like to thank all of our generous funding sources and some collaborators. And I'll leave you with this summary. So there were basically two ideas in this talk. The first is that if you set up your network with motion parameters as additional inputs, along with the corrupted case-based data, this is a helpful framework for doing motion correction. And second, when you have this set up, you can use a data consistency loss to optimize at test time and find a good value for the motion parameters, which in turn gives you a good reconstruction. Experimentally, we've shown that this strategy gives us really high fidelity, data consistent reconstructions. And in addition, when we don't get those good reconstructions, we're able to reject them via this automatic monitoring strategy. And we've shown this both on simulated data and on a realistic test example. So with that, I'm happy to take any questions.
Yep, thank you for a wonderful talk. We have a question from the floor.
Hear me now? Great. Thank you for the talk. It's really interesting. I want to ask about the data consistency modelization. You, to my understanding, tell me if I'm wrong, you assume the Cartesian subsampling there, right? So would that work under this modelization for non-Cartesian subsampling? Can you incorporate your method there?
Yeah, I think the form of the forward operator would change, but you can definitely incorporate that. So the way that would work is that US operator, which selected the points in K-space, that works on sort of a point-wise basis. So you would just change that to select if you have a radial trajectory or a spiral trajectory, like whatever points lie along that trajectory. Yep.
Thank you.
So impressive work. So you showed some results where you clearly outperform other methods. Though in the difference images, there was some signal in your reconstructions. But is it a limitation, or is that the ground truth that's inaccurate, that perhaps you're even superior over that? So how should we interpret your difference images?
Let me just make sure I am referring to the same thing. You're talking about these discrepancies that was here?
Yep.
Yeah, there's certainly some sort of leftover variation. One thing I'll mention that I think is related to this is that, so the network is trained using SSIM loss, which doesn't necessarily, like, you can have sort of these low frequency variations in sort of offsets in the reconstructed image. I think this may be related to that, but it's not sort of a structural issue in the reconstruction.
And just to point out, I think the sharpness in the delineation of lesions is superior for your method as well, so that might also be a thing to look at.
Okay.
So this acquisition is fundamentally limited in being unable to capture through plane motion, like nodding or so, right? So how, is this some unresolved issue, or do you have some thoughts on how to capture that?
So I think the acquisition we're using is actually, it's a 3D volume of 2D slices, and there could be through plane motion there. I think there's nothing inherent to our method which says you couldn't incorporate, like extend the forward operator to incorporate through plane motion, but I think certainly that's the next challenge for us to work on. Things that will make that like more technically demanding than just extending the forward operator are that the hypernetwork setup that we have for the network is pretty memory intensive, and so moving that to 3D will be a challenge. You can probably get around that by doing sort of stacks of slices as opposed to the whole volume at once. And then the other thing is that typically for these, like the through plane voxel size is much, or yeah, that dimension is much bigger than in plane. And so I think the motion artifacts will just be worse. There's probably like an inherent limit to...
Or less, even, because of the slice thickness, right?
Right, so I think if the motion is big enough that you end up going past the slice thickness, the result will be worse, but maybe you're less likely to be in that scenario.
Okay, yeah.
But yeah, there may be a limit on how well you can do there.
Yeah, thank you.
Yeah, thanks.
I think we have time for one more. Mullen?
Thanks for the impressive work and the presentation. I have one question related to the, so for the inference, you have to do the optimization for the like motion parameters, right? So I wonder how sensitive it is related to the initialization of the motion parameters when you do the optimization.
Sorry, is the question how the motion parameters are initialized?
So when you do the optimization to find the motion parameters for inference, how sensitive it is related to the initialization of the motion parameters?
Yeah, it's a little bit sensitive. So right now, I didn't get into the details of the optimization, but we basically do 4 trial runs and there's 2 things that vary. Like we start off by initializing the motion parameters to some slightly noised value, and we also have some stochasticity in the optimization itself. And we need all 4 trials, so like it is a little bit sensitive. But I think there's a couple of things we can do about this. So one really interesting direction, which I didn't talk about, is that with this setup, you basically control the loss landscape that you encounter at test time. So like we're only training with examples where you have the ground truth motion parameters as the inputs, but you could think about doing this where you also train with the wrong motion parameters, and you teach the network to output something which is even more data inconsistent. And I think strategies like that might help us with this problem and make you a little bit less sensitive to the initialization.
Thanks.
Let's thank the speaker again. Okay, so I know on your schedules it says it's about to be poster and coffee time, but we're going to stand in the way of coffee unwisely, and we'll have some announcements, and then we'll actually have teaser talks. So. Yeah.
How do I always find myself in the way of coffee? I don't know. Okay, so we have some exciting developments. You know how lunch yesterday was a little bit problematic, so we're extending lunch from 11:30 to 1, so everyone has time to go actually eat and come back. We recommend leaving here no later than noon so that you have a bit of time to do that. The keynote at 1, remember all the flight delays. They're not all in New York. They're also in Miami and elsewhere. So she's been delayed and then delayed and then delayed, and she's been taxiing for the better part of an hour in Miami. So we're going to do a little bit of a switch in the schedule. So 1 to 2, we're going to do the orals. That was meant to be at 2 to 3. At 2, we're going to have the keynote, and then the rest of the day should go as planned. So that's, again, 11:30 to 1, lunch, 1 to 2, orals, 2 to 3, keynote. Now, the 4 orals that are scheduled for that oral session, if you could come find me and tell me you've heard me say this, that would lower my blood pressure. I would appreciate it. And that's it. I'm no longer in the way of coffee. Your fault now.
I like that we clap for announcements, too. All right, if I could have all of the teaser poster presenters up here on the right. And hopefully you will all see wonderful presentations and not the presenter view. Yes, all right. Our first speaker is T13, or also known as P003. P003. If not, we'll go to the next one, which is P035.
Thank you. Yeah, so my name is Louis van Harte. I'm a PhD student at the Universiteit van Amsterdam, or the Amsterdam UMC, and I'm presenting work on deformable image registration with geometry-informed implicit neural representations. And the core idea of this work is that if you're doing registration or motion analysis, then the motion fields that you acquire or that you try to optimize for aren't actually random. These are informed by the structures and the geometry of the tissues that you want to register. And these are quite often known. So in this work, we were working with small intestines, where in the small intestine, the main motion is related to the squeezing and the peristalsis along the small intestine. So in image space, that's kind of a weird motion field that is modulated around this arbitrary polynomial. But in implicit neural representations, we can choose our coordinate systems arbitrarily. So what we did was we wrap our coordinate system around these small intestine center lines, and suddenly the motion fields are completely aligned with our axes. And that gives us a much easier field to optimize for. So when we optimize our registration in this transformation, suddenly our registrations become much easier to optimize for, and hence we get better registrations as a result. So my poster is number 16. If you have any questions, then I'll be there. Thank you very much.
Our next speaker is a poster number that I don't know, but it's P062, sorry.
Good morning, everybody. Surface-based cortical registration is commonly driven by folding patterns, such as the curvature of gyra and sulci. However, it may not accurately predict functions due to the large functional variations observed across individuals. As part of the free software team, we are trying to develop methods for better and faster registration. Here, we propose a joint spherical registration framework, JOSA, that uses separate deformations to explicitly model the differences across modalities, while automatically learning an atlas, optimal atlas for the registration. Using a semi-supervised training strategy on the bottom, where functional data are not required during inference, we are able to, the JOSA is able to achieve better registration in both geometry and function at the same time. And this flexible framework can also be extended easily to parcellations as well. If you have any question, please stop by my poster at T18 and reach me out if you have, by email, the QR code. Thank you.
Thank you. Our next speaker is P105.
Hi, everyone. I'm Daniel Pizarro from the University of Alcalá in Spain. I'm presenting our work with a collaboration with the University of Clermont-Auvergne in France. So the main objective of our work is how to improve laparoscopic surgery of the liver. And specifically, we want to register information from preparative data into the images of the laparoscopic data. And this is a difficult problem with different modalities. It's a 3D, 2D registration. We solve it with deep learning, but since we don't have data, we have to, we propose a patient-specific training using biomechanical modeling and simulations. So if you're interested in the results with real data, just please visit the poster T20. Thank you.
And our next speaker is P146.
Good morning, everyone. My name is Shunxin Bao from Vanderbilt University. So our paper is about unpaired patch-wise based image synthesis between 27 multiplex immunofluorescence markers and H&E. So once we stitch back all the patches back to whole-slide images, we will usually observe the tiling effect or edge effects among the different transition of the patches. So one of the main contribution of this paper is tries to resolve this annoying issue. It's in a computational efficient way. It's pretty straightforward and can be definitely generalized to any other synthesis scenario if you are using different modalities. Please drop by T24 right there if you're interested. Thank you very much.
And our next speaker is P161, also known as T25.
Hi, everyone. I'm Raghav Mehta, and today I'm going to talk about evaluating the fairness of deep learning uncertainty estimation in medical image analysis. So let's say that you have a model which is trained, and you do the inference, and you see that it has accuracy of 0.66. And you look at the uncertainty histogram, and you find that when the model is correct, it has low uncertainty, and when model is incorrect, it has a high uncertainty. But now if you evaluate this model, let's say based on a subgroup, let's say for male versus female, you see that there is a discrepancy in accuracy between them. So you can apply a lot of fairness mitigation method, which can make sure that the accuracy between subgroups are reduced, difference in accuracy between subgroups are reduced. But it has not been evaluated how this would affect the uncertainty associated with model output. So if people are interested in talking about this, please feel free to drop by a poster, and I will be happy to talk about multiple experiments which we did and what we found out. So thank you, and see.
Our next speaker is P165.
Good morning, everyone. My name is Mustafizur Rahman. In our paper, we have made two major contributions. One is we proposed a multi-scale hierarchical vision transformer for medical image segmentation that calculates self-attention in multiple attention windows. And we also propose a new loss regularization strategy. We have found in our experiments that this to combinedly outperforms all of the state-of-the-art methods, and we got the best results in synapse multi-organ and ACTC organ segmentation data set. Welcome to our poster presentation at T26. Thank you, everyone.
Okay, and our next one is P213.
Hello, I'm Thomas from Rice University, and today I want to talk about our work on core set-based DRB compression for lifelong deep reinforcement learning in medical imaging. So there are two problems when applying deep learning models to medical imaging. The first one is that medical imaging environments evolves rapidly. You get new environments, new images all the time. So the models need to adapt to these changes. The second problem is that the medical imaging devices are getting more and more portable, but these models are getting more and more reliant on high-end GPUs. Selective experience replay is a way to address problem one with the lifelong learning capabilities, but the ERBs, the experience replay pluggers, are computationally and memory intensive, so it's hard for edge deployment. What we do is that we improve on selective experience replay to create like a data efficient core set compression of the ERBs so that it can be deployed on edge devices. I'm happy to chat today at T28. Thank you.
Okay. And we have two short papers that were missed last time. So this is S005.
Hi, I'm Lucas Remedios. I'm a PhD student from here at Vanderbilt. So if you're interested in training a model using over 100 gigabytes of GPU RAM, there's a lot I know, on images that are over 1 billion pixels without having to patch into small little 256 by 256 patches at less than 2 minutes per batch, all for less than $5,000 US. Let's talk about it. I'm over there by the window. Yeah, thanks.
Thanks, Remedios. Our next poster is S009. S009. If not, oh, okay. One more.
Good morning, everyone. I'm Ryan Zern, and I'm an undergrad researcher from the University of Massachusetts, Boston. We're presenting a novel open source solution to tackle the issue of unwinding images in a large mammogram data set. Our two-stage hybrid approach starts with a unique 5-bin histogram thresholding technique to filter the initial data set. And for the second stage, we've implemented a variational autoencoder, enabling us to filter and refine and eliminate thousands of undesired images. This method presents substantial potential for mammogram image management. Our work is completely open source and available on GitHub. I encourage you all to check out our poster at booth T34. Thank you.
All right, that concludes the the teaser talks. We have poster session, and lunch will start around 11:30. Thank you for coming. Yeah, we'll debug during the break, basically.
When you sent the initial email about the teaser talks, I think on Sunday, I submitted mine to the Dropbox.
Okay.
Do I need to resubmit to like the session-specific links that you sent later on?
When is your poster? Is it
Tomorrow.
tomorrow? Okay.
Yeah, it's W10, I think.
Okay. I will check in a second. Let me start this rotation.
Yeah, sorry, not trying
No, no, stay there. Okay. Yeah, it's a full paper.
Yeah.
So you're presenting tomorrow morning. Yeah. So if it's in the Wednesday Dropbox, I have it already, and then I'll compile it and send out the email tomorrow morning. If you don't get an email at 6 a.m. or 7 a.m. tomorrow morning, Oh, so you submitted to your, do you have an oral? No.
If you sign up for a WISE tour and you don't know where to go, David is in the back and he's going to be leading the tour in just a minute. He is waving right now. WISE tour is starting. You don't have to have signed up. We have room. All right, coffee. It's downstairs. Yeah, so go to the back of the poster room. There's stairs up.
There's a speaker ready room, but you can also check up here. Let's do it. You're just going to be up on the display, so that's okay. Okay. forgotten that there's another screen or somehow. Yeah. Yep. Okay. Windows B. Okay. Yeah. Thank you.
This is the monitor.
Well, they're going to hear everything we're saying.
Where are we now?
And it's 12 minutes and then 3 minutes of question.
Okay. Sorry, translate.
We have to tell them to wrap it up after 13.
This one. Hmm? 1, 2, 3, 4. Yep.
We have to make sure these people are here. She's here, over there.
Okay, he is here because he had a poster presentation before lunch. This is all.
Here, I'll let you introduce that one. And I'll do these two. Ridian?
Which ones? The first two?
How's that?
Okay. And this is Rogier. This looks like a Dutch name. Van der Sluis.
Oh, perfect.
Something like that. We'll try.
You guys good? Need anything? Are
all the
are
speakers
all
here?
the speakers physically here?
Oh,
and
I don't know that, but they all told me they heard me. I feel
yeah,
heard.
just in case. It's the
Okay.
first author. Just checking that are speaking.
What's his name?
Ridian Windsor, ORJ Van.
Yeah, he's here.
Are you Ridian?
The second one, the Stanford one, is not the first author.
Which one? Which one is
What's the
the
Stanford one?
The one that has, let me see, Daniel Rubin on those
No,
ones?
it's this one here. Randall Rubin. So who is it? Oh, wait. Is it Ridian? Okay. Yeah, you can. Yeah, sorry.
So who's
I
presenting?
guess. He's Nandita. Who's presenting.
Nandita.
Yeah.
Okay. Nandita Pashkar.
Jay Chang is the first one who is presenting on the third one.
And should I have the first speaker here? And are you going to make sure that they can log into their?
We have a Daniel for this.
We all need a Daniel for that.
We even do all need a Daniel.
We're gonna take you
Yes,
home.
please.
Okay. We just need you to make sure everything's working. Do you want
Yep.
the first speaker to already be here?
Daniel. Sophie's invited to dinner officially.
Okay.
So the buzzer will.
Thank you.
Do you want him to come up?
Yes, please. Do you know the names already?
Yeah.
And I can just
Oh,
pull up
not that one.
the
Yeah.
slide. We can
Sure.
pull it up before you officially start if you want.
And do you want us to introduce ourselves?
Yes.
Oh, okay.
But
And like-
I'm not in charge. She's in charge.
Oh, do you want us to introduce ourselves? Yes, please. And do you want us to introduce the speakers here? Hello, hello. Okay. So I'll introduce. Okay.
Will you time the talks then?
We probably have 5.
He said he'll be
10
one
slides,
extra
5
minute,
slides.
but not to cut him off.
Minutes?
But the questions. It's post lunch, so already they pay a lot.
Oh
of
my
attention
God.
to the talk, so you can
Okay,
come.
let's wait 5. What? Michael Kim, yes. Is he the one driving?
Oh, it's this that that we'll have that.
Yeah. You made Michael. Oh, okay.
So they have to see the
Girlfriend, but yeah. They're cute. They're adorable. They're 23. Like, anyway. Don't. 24-year-old professor. Leave me alone. just wondering.
Yeah, ourselves.
Yeah, and introduce
You're
the
going to introduce
session.
the session. Or do you want us to do that?
I can if you really want me to. but
Wait, do you have anything you want to say?
No, there's no announcements yet.
Okay. We're just going to say welcome.
This will
to
be
the
quicker.
session.
And a reminder that they cannot see the laser on the internet. So.
Take care of it.
Right. Okay.
I think everything there,
It's fine.
everything technical, not everything.
It's on.
Is there a dispatch? Okay, good. That's busy. I know. It's so near. It'll be over soon. Yeah, sure.
Hello, hello.
Okay.
Okay, welcome everyone to the afternoon oral session. We have 4 talks in this session. I'm Tal Arbel from McGill University in Mila.
Hi, good afternoon, everybody. I'm Francesco Ciompi from Radboud University Medical Center in the Netherlands.
And we're going to be chairing the session. So our first speaker is Ridian Windsor. And the talk is Vision Language Modeling for Radiological Imaging and Reports in the Low Data Regime. So thank you.
Hi everyone. So yeah, I'm Ridian. I'm from the Visual Geometry Group in the University of Oxford, and today I'm going to be presenting some of our recent work on adapting vision language modeling methods to medical imaging. So I'm sure you're all aware there's been significant progress in vision language modeling. That's models that work with both images and text as input in recent years. And I think that's really exciting to us as a medical imaging community. So in this work, we're going to look at what's called a dual encoder setup, a dual encoder vision language model, which you can see on that figure there. Essentially, we have 2 models, an image encoder and a text encoder. The image encoder will take our scan as input and output an embedding vector, and likewise the text encoder will take a free text radiological report. And we want to train these models such that we have very high cosine similarity between text and image embeddings which match each other, and very low similarity if they don't match. So obviously a big advantage of this means that potentially it means less manual supervision, manual annotation from radiologists. But I think there's a couple of other advantages too. One of them being that free text is probably a much more flexible way of representing clinical findings in a scan, because we're not restricted to a fixed set of classes, and we can better capture the complexities and the interrelations between all the possible diagnoses. But we're going to run into a big challenge, and that challenge is that general vision language modeling methods are trained on data sets that are gargantuan, far larger than we would see in medical imaging. So CLIP, which I'm sure you've heard of, is trained on 400 million image-text pairs. Clearly, this isn't going to be feasible in medical imaging studies. So what we did in this work is we took these vision language modeling methods and we tried to adapt them so that we can work with much smaller training data set sizes, more on the sort of scale that we'd see in our research. And there's 3 main approaches we take to try and scale these models down. The first is asking the question, can we take a model that's been trained on a large generic data set and adapt that to whatever task we're interested in? The second is looking at different similarity metrics to compare any given image and text. And the final thing we looked at is, can we add in additional supervision to our loss function and hopefully stave off overfitting for a little bit longer? So I'll go into each of these in detail, but I think first it's worth talking about how we'll evaluate our models. In this case, we're interested in models that can accurately classify if any given report and scan match each other or not. And we're making the assumption here that if it can do that task very well, that'll transfer to whatever downstream task we're interested in. What this means in practice is we measure the similarity between every single image-text pair in our test data set split, and then we can plot a receiver-operator curve, and we're going to try and maximize the receiver-operator curve. So you'll see lots of curves like this during the talk. What this shows is several different models, each with different training data set sizes, which is shown on the x-axis, and the y-axis shows the test performance. And what we want to do is drag up these points on the left-hand side of the graph so that we have less of a fall-off in performance as we use less and less training data. So we want this to be general to lots of different types of imaging modalities, so hopefully everyone can take something away from this talk. But for the purposes of the experiments, we're going to use these chest X-rays and reports from Mimic CXR JPEG. And the reason we use this data set is it's publicly available, and it's very big for medical imaging, which means that we can see how these methods adapt to a range of different training data set sizes. So our image text tuples look like this. We have a frontal X-ray and the impression section of the report, which is a 2 or 3 sentence summary at the end, which kind of summarizes the main clinical findings from that investigation. So as I said, the first question we explored was, can we leverage these models that have been pre-trained on large generic data sets? So we'll use a ResNet architecture for the image encoder, and for the text encoder, we'll use a BERT architecture, and we'll try a range of different pre-trained models, including random initialization, ImageNet weights, and the CLIP image encoder for our image encoder. And for the text encoder, we'll use a vanilla or a standard BERT model, the CLIP text encoder, clinical BERT, which is very similar to the standard BERT, except for it's trained on clinical notes and medical abstracts, and finally CXR BERT, which is trained on radiological reports. So first we looked at varying the image encoder with a fixed text encoder, in this case a standard BERT model. This is the CLIP baseline, so this is using a CLIP image encoder and a CLIP text encoder. And if we use a randomly initialized ResNet, we get much worse performance, and this makes sense because CLIP has a pre-trained image encoder, whereas obviously we don't here. This story holds if we use ImageNet trained model. So here we have two generic image and text encoders trained on very large data sets, but they don't do fantastically on our task because of the domain gap. This is a similar result for varying the text encoder. Don't worry about what the image encoder is at the moment here, just know that it's fixed between all these curves. So if we use standard BERT, we get this curve. If we use clinical BERT, we get a little bit boost in performance because we're getting closer to our target domain. And CXR BERT, which is the closest to the target domain, gives us the best performance, particularly at those lower data set sizes that we're interested in. But we didn't want to stop there. We thought, can we take these models and get them used to our target domain? So in this case, we use unimodal self-supervision on our training data to adapt these models to the task we're interested in. So you can use any form of unimodal self-supervision here, but what we've done is we've taken a pre-trained model, done some unimodal self-supervision on the X-rays and the reports, and then we only do the VLM training after that, and in the hope that the encoders will get used to the distribution of data that they'll see during VLM training. And we find that this is beneficial both for the image encoder, so this top curve shows when we domain adapt that ImageNet pre-trained ResNet, and it also is true for the text encoder. So I deliberately skipped over the self-supervision methods that we used there. Feel free to ask questions, but that was just in the interest of time. But the point is you could use any self-supervision method. The takeaway is if you're going to do multimodal VLM training, try some unimodal self-supervision first. So the second thing we looked at is different similarity metrics to compare a given image-text pair. So far, we've looked at what's called a global loss function, and this means we represent both the image and the text as a single embedding vector and try and maximize the cosine similarity between them. But an alternative is what's called a local loss function, and here we represent both the text and the image as a set of vectors. So you can imagine a vector corresponding to each token in the text, and different vectors corresponding to different image regions for the image encoder. And we then maximize the token-to-patch similarity instead. So this could be used as our main contrastive loss function or as an auxiliary loss. And we tried both. So this is our baseline before with the best domain-adapted models. And if we add in a local loss function, in this case we're using Gloria, which is a popular local loss function from the literature, we get a little bit of a boost in performance, which is nice. But of course, now we've got two ways of measuring similarities, either by comparing the global embedding vectors or by comparing the local embedding vectors. And we find that if at test time you instead measure the similarities between the local embedding vectors, you get a big boost in performance represented by these dotted lines here. Now, this isn't quite a fair comparison between comparing global embedding vectors because in the global embedding vector case, you have to compress it into quite a small dimensionality. But if you're specifically interested in the task of, can I match this image to this text, probably a local similarity metric is the way to go. So the last thing we looked at is adding more supervision during VLM training. And we were inspired by this paper by Lee et al., which is called DClip, or data efficient clip. And this introduces a couple of new terms to the contrastive loss function, which can broadly be separated into two categories. The first category being adding unimodal self-supervision, just like we saw in the domain adaptation step in the first experiments. And the second thing we can do is create new positive image-text pairs, either by augmenting our images, augmenting our text, or finding the nearest neighbors of our images and text in an embedding space. And I'll come to that in a second. So to give you a concrete idea, we sample our batch of reports and images. We apply our unimodal self-supervision, so text-only and image-only self-supervision. In this case, we're using SimCLR for the image self-supervision and masked language modeling for the text supervision. And we have two image-text pairs here from the two augmented images from SimCLR. So then we can apply either our local or global loss function here. But we don't just have the ability to augment the images, we can also augment the text, which we can do through randomly replacing words with synonyms, deleting words, switching them around, etc. And hopefully you'll get a report that looks slightly different but has the same semantic content. So that gives us two more image text pairs. And the final thing that we tried was this nearest neighbor embedding search. So as you're training your model, you cache the report's embeddings, and hopefully when you sample a report and project it into embedding space, the other reports that have been projected to similar areas in embedding space should match the same set of images, and thus they would have the same semantic content, hopefully. And we find this to be true when we look at them after training these networks. So again, if we train this model, we get a boost in performance from using each of these different components. And there's an ablation study for each step here in our full paper. So we know that every single term in this loss function is contributing. So you get a boost in performance, particularly at low data set sizes again, which we're most interested in, and it works additively with local loss functions as well. So again, we get better performance. So this is just a summary slide of how far we've come. We found the best initialization of our networks, hopefully. We found new ways of measuring similarities between image text reports, and we've looked at adding different terms for supervising our networks. And that's given this boost in performance, which is really encouraging and what we wanted to see. So the final question is, well, that's all very well, but does that transfer to clinical tasks that we might be interested in? So the last part of our paper was related to this. We took the image encoder trained by our best combination of methods, and we performed linear probing on that for a range of different conditions related to chest X-rays. And what we find is that when we do this linear probing, our model performs as well as a CLIP model fine-tuned on our data, which has been trained with 5 to 10 times more data, which was the original aim of the project. So we were really pleased with that result. So I've got a final slide on takeaways for when you're training your own vision language models, and I would really recommend this, by the way. It's been a ton of fun. I was a little bit scared by using text data, but it's actually very easy, much easier than images. So the first thing is, when you're initializing your model, try unimodal self-supervision first, and you'll get a boost in performance. The story of local or global loss functions is still a little bit unclear, but generally adding a local loss function as an auxiliary loss can't hurt. And the final thing is there's plenty of ways we can add more supervision into this. And I think there's even new ideas beyond what we've done here that means we could get even more out of our contrastive loss function. So thank you very much for your time, and I'll take questions.
Okay, we're ready for questions. Please come up to the microphone if you have a question. Thank you so much for this really interesting talk. I was just wondering myself if how you actually computed your local areas for your local losses. Like you just did a grid?
Yeah, sorry, I did okay. Speed over that bit. So what you have is a series of vectors for each token in the text and a series of vectors for each token in the image. And then you can calculate the pairwise similarity. Okay. And then you do a softmax over those similarities. So that tells you this part of the text is probably related to this bit of the image. And then you sum over all those pairwise comparisons.
Yeah, I'm wondering what your thoughts are about going forward, maybe, because as you can see with the grid, it corresponds to half of one lobe of the lung or something. Is there a way we can look at sort of local regions that are more tightly related to features that might...
Yeah, so this is just a visualization. In actual fact, there's many more than 6 vectors coming from the image encoder. Okay. It's just to make it clearer. So you basically just have a spatial feature map, and then you take the channels from each of them.
Okay. All right, thank you.
Cheers.
Okay, we have a question. Yeah, go ahead, thanks.
Hi, great talk. Just a quick question about the positive, basically the positive pairs for your text and image augmentations.
Yeah.
Could you comment a little bit more on the strategies you used and other potential strategies that you thought of?
To find the pseudo-positive pairs?
Yeah.
Yeah, okay, yeah, that's a good question. So, so we have augmentation. If we augment an image, it should still match to the same report. And likewise for text, there's lots of different ways you can try text augmentation. One thing I tried quite a lot and didn't get to work, unfortunately, but I think would be quite cool, is using large language models to augment text. So give me a report with the same clinical findings in a different reporting style. So that gives us some more positive pairs. And then the last thing we did, as I said, was when you're training the model, you have to project the reports into a joint embedding space with the images. So if 2 reports are projected to the same point in embedding space, hypothetically, that should mean they match to the same set of images. So that would mean that they have the same clinical findings, even if their reporting style differs. So you can, and again, there's lots of figures in the paper to show this is true, that you get reports that say, different in length, different reporting style, but generally, they might both have pleural effusion or both have fractures, whatever the findings are. But I think there's more work to examine that embedding space, and we were quite crude about it, I think, in the paper, and you could definitely, it's an area of research that could definitely be pursued.
Awesome, thank you. Just one follow-up question if I have time. So basically when you when you do get these positive pairs, do you so every time you have, how long do you expand it to? So for instance, for every image augmentation, do you have all text augmentations, and for every text augmentation, do you just scale the training set a lot based on these type of augmentations, or do you selectively choose some of them that actually work well?
Yeah, so there's no choosing pairs. These are all generated on the fly during training. So you see the loss function is exactly as shown here. You have 6 image text pairs and the self-supervised loss terms. And then, afterwards we looked at it. But it's all on the fly, so you don't, I think probably at the beginning of training, particularly with the nearest neighbors, you're actually just getting a lot of noise in your training signal. So probably the optimal way to train these models would be get rid of that nearest neighbors term originally and then introduce it as your network's kind of getting a grasp on things. But we didn't do that, and it converged anyway, so it was fine.
Thank you.
Okay, let's thank our speaker. Okay, our next talk is about learning to compare longitudinal images, and here to present it is Hee-Jong Kim.
Hi, I'm Hee-Jong Kim, and I'm working with Dr. Mark Sabanku at Cornell University, and I'm going to talk about learning to compare longitudinal images. So longitudinal study involves the longitudinal data, and the data measure multiple times in different time points from the same sample or same subject. And in medical imaging, there are different studies ongoing. That includes aging and disease progression, and development and treatment progression. And this work specifically, it's motivated by this clinical collaboration with Dr. Nagar from Weill Cornell. And we wanted to look at the treatment progression, but even with the expert's eyes, it's really hard to tell the difference. You see in the figure on the bottom right. So motivated by that, we thought maybe using the deep learning, and if we can look at the pairwise image comparison, and if we can tell something with a large-scale data set, maybe could find something interesting. So that's our motivation. And longitudinal images, typically it has many things change between scans. And some are nuisance, and some are clinically and biologically relevant. For example, if you look at the brain imaging, and if you're looking for some aging effect, the patient movement or the image orientation of bias fields or some noise effects are the nuisance factors. And the cortical thickness or the ventricle size changes, they are the clinically biological or biologically relevant changes. So the core challenge here is we want to sort out what's relevant from the other stuff. So there can be 2 questions. The first is characterizing the population level temporal dynamics, meaning that we are looking for some population change. So in the example of the brain, then it will be the brain aging changes. It will be the cortical thickness changes, and in the average, there will be a population average that says that it will increase or decrease. And for the second question, it will be quantifying and localizing individual level change. That means that even if we can find the population change in average, there can be some individual variability. For example, in the cortical thickness change, everyone can have different pattern of changing. So classical approach to solve this question, there are typically 2 steps. The first is they normalize the nuisance variation using the pre-processing step. for example, the image registration or the segmentation. So once they have the segmented part or the coordinate thickness, for example, extracted from the MR, they use the statistical modeling to look at the longitudinal changes. But using this classical approach has some limitations because it is largely dependent on the pre-processing steps, and the pre-processing steps quality, it will affect the final results. And also it depends on the modeling as well. And recently there have been deep learning approaches to study longitudinal changes. These are the two papers from 2021, and both results, the longitudinal self-supervised learning and the longitudinal variation autoencoder, they could capture these longitudinal changes, and also they could have this successfully find latent representation to represent the longitudinal data. But their loss is depending on the image reconstruction loss. So to use the image reconstruction loss, they assume that those images are aligned, and the alignment quality will affect the final results. In our approach, we assume that the longitudinal changes is time irreversible, for example, development or aging or degeneration. And then we train a model to time order the longitudinal images. And by examining where the model is paying attention to, then we can find the meaningful changes within the images. And also by looking at the prediction value, that can be used as confidence in the time ordering, which can quantify the longitudinal chance. So to give you some more details, this is how our architecture looks. So we focus on two different scenarios. So these two scenarios are trained separately. So the first scenario is we wanted to capture the temporal change. So in this example of tumor, so given a pair of image, the prediction value, we will try to predict the size of the tumor, the size difference of the tumor. Then that's what we call supervised here. And the second scenario is the temporal order, which we call self-supervised. And in this example, it will try to predict the order of this image, so which one came first. To give you some details of this architecture, so given a pair of image, it will fit into a feature network, which is Siamese. And we're gonna get a feature vector, and we subtract the vector to fit into the fully connected linear layer without the bias. And by doing so, we can get some advantage, which is we can keep this network as ranking network, and we can keep this characteristics of ranking network. That includes reflexibility, antisymmetry, and transitivity. So using this idea and architecture, we try to validate our idea using these 4 different experiments. First is Starman and embryo and synthetic tumor and brain aging. So the important significant change that we're looking for each data set is for Starman is raising left arm, the embryo is developmental phase, as you see in the cell division changes. And for the synthetic tumor, the tumor size will increase over time. And for the brain aging, it will be the brain tissue area that's relevant to the brain aging. So as a quantitative analysis, we look at the correlation between the ground truth change in the target variable and the predicted change. So the plots that you're looking at on the right is, they are the scatter plots, and the x-axis is the ground truth change, and the y-axis is the predicted change. And the number in each plot is a Pearson correlation coefficient, and that represents like how much the predicted value is correlated to the ground truth. So in overall, the PairNet results are consistent with the ground truth, and it has a high correlation value compared to other baseline methods. To highlight some results, the pairwise supervised result is similar or the better than the cross-sectional regression. And to get the cross-sectional result, we use the same architecture, which is ResNet, and, but without the Siamese part. So it will directly try to predict the size of the tumor, for example. And what this result shows us is that the cross-sectional regression can be a challenging task. And another result highlight is when we look at the self-supervised and compare with the baseline method, our method could outperform those baseline methods. And the third result, which I like the most, is the supervised pair net and the self-supervised pair net. The correlation was really similar. And what this indicates maybe is even without the actual label, even without the actual, for example, the tumor size change, by using only the ordering, we might be able to find something interesting from the longitudinal data. So for the qualitative analysis, we look at the weighted CAM, the class activation map, and the weight is defined using the last layer's weight and also the feature difference. So it's basically weighted CAM. And overall, if you look at the result, what we should look at from this figure is the Starman raging arm and the tumor location, and also the embryo location. And for aging brain, it should be inside the brain, and also mostly it highlights the posterior part of the brain where the ventricle is located. And the ventricle size change is known to be associated with the aging. So to highlight some results, this is the aging brain result from the self-supervised pair net. And the self-supervised pair net could focus on the, as I said, the posterior part, and also it could neglect the other superior changes, like the brain movement or the outside the brain, which is the skull part. And, but the LVAE method, which is the baseline, and this result is using their implementation of finding the latent representation. The blue is the negative gradient, and the red is the positive gradient. But if you look at the result, it's highlighting the skull part while still they're looking at the brain inside. And this is another example. So when there is the huge movement or inter-subject variation, the pair net could still find the right embryo location, but the baseline is failed to find where they should look at. So we have some weaknesses. The first is the longitudinal studies. They don't only consider the time irreversible changes, but in this study, we only focus on the time irreversible change. And the second, PairNet cannot disentangle the multiple temporal processes or non-monotonic temporal changes. So if the disease is happening and the aging at the same time, we cannot disentangle these two factors. And better architectural choices exist. So instead of ResNet, we might be able to use a transformer that incorporates those cross-image detention mechanism. So as future work, we can use the clinical measurement for the self-supervised learning instead of the delta time. And also, we can use a different architecture. Also, we can even use architecture with the pre-processing. And I think that might help the model to alleviate being distracted by the other nuisance factors, and then focus on the changes only. And other future work that can work out is we can encourage more exhaustive change detection, so we can have more localized localization result. And as ongoing work, we're currently working on applying this method to 3D brain images, the brain MR images for studying the aging brain. And we made some modification in the architecture, and we could see that they can work better localized. They work better on localization. So it's ongoing work, and hope I can present something next year. And This is under my talk, and thank you for listening. I'm happy to take any questions.
Thank you for that really interesting talk. We have time for questions, so you can come up to the microphone. Maybe I'll start. I was just wondering, you answered some of my questions with your future work, but I was just wondering about, have you looked at sort of how subtle those changes need to be between two time points for you to be able to detect it? You know, let's say it's a few voxels in one direction, or can you right now just look at big changes between two time points?
I assume even if there's a small changes, as you see in the video right here, it could find something. So it could highlight something.
Okay.
Yeah, but I didn't have like quantitative measure. But you might be able to find some table in the appendix. There's a table over there.
Okay, thank you.
Yeah, I also have a question to follow up a bit. So what you're showing here, I understood it's a simulated brain tumor, right?
Yes.
So have you tried to apply your method to a pair of images with an actual brain tumor, maybe of different sizes?
If it's always like increment changes, I think it's possible to be applied. But if sometimes the tumor increases and they sometimes decreases as well, right? In that case, it's hard to capture those changes because we assume that this is monotonic changes. That's kind of a limitation.
But you expect your model to apply well also on real data instead of simulated tumor?
Not at the moment. Like if we have data, like we are happy to explore that. Yeah.
Thanks.
So in this image, sorry, the rest of the brain remains fixed, right? It's just the tumor that's changing?
Here, yeah, the
okay.
synthetic tumor, yes,
Okay.
yeah. I just fixed everything, but tumor size is the only thing that's changing.
Okay. Any other questions? So let's thank our speaker.
Right, then we continue with the next talk. The title is Exploring Image Augmentation for Siamese Representation Learning with Chest X-rays. And I understood that the speaker is the second author of the paper, Nandita Bhaskar. Hope it's correct.
Yeah. Hi, everyone. It's my pleasure to be here at MIDL, and thanks for the kind introduction. This is joint work with my co-first author, Roher van der Schlaa, and cannot be done without the support of our advisors, Daniel, Kurt, and Akshay. So I guess this is kind of a little late introduction since it's the third talk, but let me still give you a primer on self-supervised learning. So what is self-supervised learning? It's basically a pre-training strategy where you're training without any explicit labels. So for instance, if you take this kitten, you want your model to actually be able to identify that this is a kitten, but instead you're training it on a different task. So you're rotating the image of a kitten and then asking it to predict the rotation. Or you're changing the color of the kitten and then asking it to predict the colorization. So the goal is you're doing these kind of tasks will kind of help the model to learn high-level representations that can be adapted for further downstream tasks. And one form of self-supervised learning is something called as Siamese representation learning, where there are basically a dual branch architecture, and it's an extremely powerful and empirically very successful form of self-supervised learning. So in this case, it essentially learns by identifying if two views or augmentations are similar or different. So let me give you a little more context into this. So let's take one Siamese network in consideration. So this is SimSiam. So it has two identical weight-sharing branches. So if we want to classify chest X-rays, we first take a chest X-ray and then make two different augmentations of it. And then it's passed through each branch. And then essentially, we're trying to make sure that the embeddings from the projector is the same as the embeddings from a predictor of a different branch. So you're having this cross-branch similarity. And out of all of these things, you've realized maybe there's one common denominator, which is augmentations. So all types of SSL kind of rely on these augmentations. And specifically, Siamese representation networks, their success relies on these pairwise augmentations that are chosen by us, the designers. And So these kind of augmentations decide what the model needs to be invariant to. So what should it be robust, and what should it actually retain for further downstream tasks? So this is all common for all natural vision tasks. So what about medical imaging? What augmentation should we actually use for medical imaging? Till now, most medical image data sets are treated as ImageNet extensions. So pretty much we use the same augmentations that we use for ImageNet. And in reality, they are very different. In fact, each modality within medical imaging is very different and might need specific set of augmentations. And unfortunately, there's been no systematic evaluation of these augmentations that work for medical imaging. And in this work, we are focusing on chest X-rays. So we deal with a bunch of these commonly used augmentations, and we propose a few of our own augmentations. And so in this case, we have the popular augmentations like crop and resize, rotate, or cut out, where you actually mask out portions of the image. And then we also propose something called a pixel distortion, which is essentially enhancing the brightness or contrast, which is a very simple task, but so far it has not been used in the set of Siamese representation learning augmentations. And we actually do a lot more augmentations as well, so if you're interested, come talk to us in the poster. So when we are training these self-supervised models, we follow the paradigm of a foundation model. So essentially, this means that we do this pre-training and then an adaptation to a downstream task. So the first stage in our pipeline is the self-supervised pre-training, where we do use the SimSIAM architecture for training our model. In the second stage, we take the pre-trained encoder from the previous step, and then just freeze it, and then just add a linear classifier on top. So now with a few examples, you can now do a supervised training of your entire model. This third stage, what you do is you take the pre-trained encoder, and you take the trained classifier that you've trained before, and then fine-tune the entire network on these labeled examples. And we kind of want to evaluate how this works in real life and whether it's actually robust to a bunch of different things. And to that purpose, we model this task as a multi-label classification and evaluate it using the macro AUROC. And we use 3 different distributions of data. So one from Mimic, chest X-rays, which is really high quality DICOM data collected in and around Boston. CheckSpurt, which has low resolution images collected in and around Stanford. And WinDR, which is a really good evaluation data set, which has actually been manually annotated by radiologists in Vietnam. So the result, or the main takeaway, is that we tried so many different pairs of augmentations, and the best pair actually is random crop and brightness and contrast pixel distortion. So if there's one thing that you'd want to take away from this talk, is that if you're training a chest X-ray classifier, these are the 2 top augmentations that you need to be aware of. So apart from all of this, chest X-rays, in general, instead of just using them to improve performance, models typically suffer from a few challenges. For instance, some of these labels are not very good quality. And more importantly, models are actually sensitive to various distribution shifts, so between different hospitals, different populations, and even different disease conditions. And something that folks don't really delve into is that these models are highly sensitive to class imbalance. So in this figure, you can see that there are certain conditions which are just 2% or 5% of the data, versus some are nearly 20% of your data. And these minority classes usually suffer in large-scale models like this. So in our approach, we wanted to evaluate how good our augmentation strategy is compared to fully supervised methods for overcoming these robustness challenges. So let's take a look at our baselines. So we trained a fully supervised model from scratch, and also with ImageNet pre-trained weights. And we do this linear probing and fine-tuning on top of it. So we find that there's almost a 10-point improvement in AUROC just by doing this pre-training and fine-tuning. So this is on the same distribution, so there's no distribution shift occurring as of yet. But what happens if we do have a different distribution? So when we evaluate it on CheckSpurt, which has a difference in quality, and on WinDR, which has a completely different population, so we see that the linear probing and fine-tuning actually increase performance than just the fully supervised models. And again, in the order of 10 points and 13 points of AUROC. So the takeaway is that when you do this linear probing and fine-tuning approach, it actually generalizes better to new environments than if you use like fully supervised models. And I talked a little bit about minority classes. So let's actually look at how this approach helps minority classes like fracture and pneumothorax. So you can see that a fully supervised model actually has almost near chance, like random chance, if it's not fine-tuned. And when we do this fine-tuning, we actually get a 15-point improvement in AUROC, which is like very promising because now it can be leveraged for like different classes and different populations as well. And finally, we also want to test like how many labels do we actually really need. So in label efficiency, we kind of want to fine-tune with 1% of the labels, maybe 10% and 50%. And we see that when we do have just 50% of the data, we're achieving the same performance as when we have 100% of the data. So this kind of suggests that this entire paradigm is pretty label efficient, which is good news for all of us. And finally, I'd like to highlight one key result. So WinDR, apart from being a completely different population, also presents a new set of pathologies. So for instance, the models trained on Mimic or Chexpert, like they don't actually encounter any tuberculosis cases because prevalence of tuberculosis in the United States is very less. But in comparison, in Vietnam, where WinDR is primarily collected from, the tuberculosis occurs, it has a really large prevalence. And we see that like when we actually do this fine-tuning, linear probing and fine-tuning, it improves performance for these unseen classes as well, which means that our model is actually now more generalizable to different pathologies, which are actually out of distribution for the model. And in summary, the optimal augmentation strategy for chest X-ray classification is the combination of random cropping and brightness contrast distortion with optimized hyperparameters. And I'd be happy to answer how exactly we do this optimization and how it differs from natural image random cropping. And the resulting foundation model that we train is actually very robust and label efficient, and it generalizes well to different environments and populations, improves minority class performance, and also to out of distribution pathologies. And it's also label efficient. So overall, it outperforms fully supervised models in all aspects. So with that, I'm happy to take questions, and our paper has associated code with it, and feel free to reach out to me if you have any questions. Thank you.
Thank you. Interesting talk. We have quite some time for questions. Do we have questions from the audience? Yeah, Ram.
Yes, thank you. I have a clarification question. I was trying to find it in the paper. So you give area under the curve all the time as performance metric, right? So what is your negative class then? Because it's a multi-class problem you're addressing, I think.
Yeah, so we treat it as a multi-label classification. So basically, it's like one versus all. So each disease, you're basically detecting whether is it present or is it absent. And then your macro AUROC is just like the macro average of all the like class-wise AUROCs.
Did you check what the comparison to radiologist is? Because for some subsets of these data sets, it has been double read by some readers.
Yeah, so this WinDR like data set has actually been radiologist annotated. So that's like a really good data set where 5 radiologists have like actually annotated this image. And we found that we didn't actually look at the like inter-radiologist comparison yet, but that's a good point, and I think we should really do it. But these labels are with the ground truth from the majority of the radiologists.
Yeah, okay, but would be interesting, right?
Yeah,
because
definitely.
0.8 for saying tuberculosis versus any other chest X-ray to me seems like really low performance. But yeah, if you have 5 human reads, so you could get an indication whether this is actually competitive to all the many products that are already out there for these things, right?
Yeah, absolutely. Yeah. Thank you.
Thanks.
Yeah, thanks. There are more questions over there.
Thank you for your nice talk. I have a question regarding this like optimal augmentation strategy you chosen. So does this augmentation work for other modality of the data? Like you applied it for X-ray images, okay?
Mhm.
So do you think it will also applicable for other modalities?
So that's a great question. So I think this strategy will work for all modalities. So actually doing this exploration, but this set of specific augmentations, we are focusing it for this particular domain of chest X-rays. So without actually evaluating our hypothesis that we need to actually get domain-specific augmentations for each modality. And in fact, we are working on some for CT and MRI as well. So this would not be the same strategy that you use for any other modality.
Okay. So I have one more question.
Sure.
I maybe missed it. Like, how do you actually choose this augmentation studies? By experimental or empirically, or do you use any sort of learning algorithm to choose this, like augmentations?
Yeah, that's a great question. So in this work, we chose it empirically, and also we proposed several new augmentations based on our knowledge of the domain. But in general, for CT and MRI, we are looking at domain, we do it empirically, but we are trying to get those augmentations based on a physics-based approach. So we have a hypothesis about what augmentations will work and when should they work, and then design those augmentations. We do not use a learning strategy to learn on the fly for these.
Oh, okay. Thank you. Thank you so much.
Yeah.
Hi, thank you for sharing your insight. I have a question about label efficient part. Can I see that?
Oh, yeah.
Yeah, sorry, I forgot the. Yeah, so for label efficiency, you have used the 50% of the labels you have. Does it mean the 50% labels are the full data set you have for the mimic CXRs?
Yes, so 50% of the labels for Mimic and 50% of the labels for WinDR.
So how many data set would that be? How many images?
So for Mimic, it would actually be still quite a bit. For WinDR, it will be around 9,000. So actually less than. So we use 15,000 images for maybe training. So 7,500 for WinDR. And then for Mimic, the training sets half of it.
Okay, so my question would be that, so in the real world, when we do our research, we wouldn't be able to collect all those kind of numbers of data for our research.
Mm-hmm.
And would the label efficiency be similar if we have a number of the data is limited to 1,000, 1,000 or lower than that?
Yeah, that's a great question. So I think we can purposely make this a little bit of a few-shot adaptability, but right now it does involve a little bit of labels. So you might see a slight performance drop when you have lesser number of labels. So for instance, if you use, when you compare the WinDR table fine-tuned with 1% of the data, so that's probably comparable to the regime that you're talking about. And so you see that there is a performance drop from what can maximum be achieved with 100% of the labels, but it's still much better than what you get from a fully supervised model. So I think it's important to keep in mind that what could be achieved more, and also with the quality of the label. So if you are selecting really hard examples to label, I think that might also boost up your metric really well, because if you're fine-tuning with really important labels, that might actually give you a better performance than randomly sampling.
Got it, thank you.
Okay, I think we have still time for one last question.
Thank you for allowing it. Great talk. You showed some interesting results where you were just doing fine-tuning on a single class. Did you guys consider studying the effect of how it goes when you increase the number of classes? Like the gain in performance, it increases or decreases as you increase the number of classes? Some insights would be nice.
So when you say increase the number of classes,
for example, you were doing rib fracture, etc. Right. So there are multiple classes in those data sets, right? So that was just one, but if you increase those, that's what I mean.
Yeah, so actually, so for instance, these 3 classes are not in the Mimic set. So the figure I showed before, it doesn't exist in that. So we added these 3 classes for WinDR.
I see.
So I think one of the strengths of this method is that it is flexible enough that you can adapt to more classes or the classes that you want without too much overhead. So you just need to retrain the final classifier layer instead of changing everything else in your model.
Okay, thank you.
Okay, thank you. Let's thank our speaker again. So we have our last talk in this session with title Self-Supervised CSF in Painting for Improved Accuracy Validation of Cortical Surface Analysis, and will be presented by Yacheng Wang. I hope I pronounced correctly.
Hello, everyone. My name is Jiacheng Wang, a PhD student in the medical lab at Vanderbilt University, supervised by Dr. Yipai Uz. Today, I'm presenting my work titled Self-Supervised CSF in Painting with Synthetic Atrophy for Improved Accuracy Validation of Cortical Thickness Analysis. This work is co-authored with Dr. Katie Larson. I would like to start by, it's not the right version. I'm sorry, I will. Let me see, this one, okay. Okay. I'm gonna start my presentation by looking at cortical thickness change, showing the diagram on the bottom. It's a super crucial biomarker in aging, Alzheimer's disease, and Huntington disease. So researchers investigate methods to measure the cortical thickness and monitor its change. You can see from the diagram on the right, the distance between the outer red surface and inner blue surface is the thickness we'll obtain from the brain. More importantly, how can we validate measurement methods when we lack ground truth and ground truth of how much the real change is? Several previous work study how to create synthetic data set with non-cortical thickness change, and we summarize them as registration-based synthetic atrophy methods. This RBSA, including our own previous work, explores this topic by using deformable registration, which achieves state-of-the-art performance for cortical thickness evaluation. For example, if we have an MR image, we can get its pixelation from it, subtract the atrophy region, and apply some mathematical function so that we know the change of cortical thickness. Lastly, we deformably register the atrophy region back to the original image as shown in the animation. We can see clear gray matter shrinkage, aka gray matter atrophy. However, registration-based atrophy methods do suffer from certain limitations. Firstly, as it is illustrated in the atrophy region, blurry boundaries may occur due to subpixel interpolation from registration. And more crucial is when we deal with deep and narrow sulci, which is the folded region in the red arrow, it's difficult to simulate realistic atrophy as it's hard to resolve the CSF with limited reference. So, to counter this limitation, we propose to use image in painting method, which of course deep learning based, to generate realistic atrophy region, which is the CSF part. And our aim is to generate clear and plausible boundary, avoiding blurry issue for better synthetic result. In painting method is widely used in 2D image, and we try to adapt it to 3D medical imaging research. Our work also hope to get insight of how can we process the 3D data, how can we obtain a large number of training samples in order to train a robust model, and how can we adapt the model to unseen data set. And I would like to walk through our proposed solution and hope you can better understand this topic after this talk. I would start by summarizing our pipeline. Our goal is that we want to obtain a non-cortical thickness change data set by synthetic atrophy method, RBSA. And we would like to use deep learning method rather than registration-based to obtain more realistic based on realistic boundary. But, however, we lack the ground truth, which make our training the model directly not feasible. That's why we divided our main pipeline into 2 stages. In the stage 1, inspired by self-supervised learning, we use volumetric random dropout method to generate tons of random samples with dropout region containing all types of tissues. Training the model is more generalized than our desired job, as our goal is just to restore the atrophy CSF. And this method allows us to use original input as our supervision. Then in stage 2, we can achieve our goal by applying the trained model to restore the CSF, even if the atrophy region lies in deep and narrow south side regions, shown in the red box. And we also designed a stage 3 to deal with unseen dataset, which take the advantage of self-supervised pre-training. Due to the limitation of time, I can show more detail in our poster session. Please stop by at T06 after this talk. Let's move on to our method detail. First, to generate a large number of training samples and utilize image itself as ground truth, we adapt this patch-based dropout to have a random number of rectangular regions containing all types of tissues. Using this, help our model to better learn what the boundary between each tissue should look like under different circumstances. And of course, we can generate arbitrary numbers of samples to help our training feasible. To better enhance the input features, we also explore how to expand the input channel into 5. Besides the input dropout from T1 weighted image, we add its counterpart, like FLAIR image, with dropout as input. We also utilize the whole brain tissue labels from FreeSurfer to help our model get a sense of semantic information. And we have the dropout region of the label to give our model more pronounced regional information. Last, as we care about the boundary, we also adapt the canny edge detection to provide more boundary information for the model. Besides the input channels, we also try to make the input features can achieve robust performance in multi-scale. We found previous research study how to integrate the sinusoidal positional encoding to image domain, which is originally developed for language model. And we leverage the use to 3D MRI image data in our paper. And of course, we care about the loss for training our model. Besides the commonly used scan loss, reconstruction, and adversarial loss, we redesigned the 3D version of perceptual and style loss for better generation results. Now, we can take a look at our model performance. We first look into the reconstruction result from restoring the drop patch in stage 1. We use 3 commonly used matrices here and evaluate on 6 subjects with 2 time points from the public available Kirby dataset. For here, we use a simple CNN backbone in 3D and compare our model with 2D CNN and state-of-the-art Llama, which is the state-of-the-art in-painting method. We also re-implement this 2D method into 2.5D, and we see that by using 2.5D, which provide more spatial information, making the performance in all metrics increase a lot. And we also noticed that even though our 3D model didn't perform well in L1, but it achieved better performance in PSNR and SSIM. We further did ablation study on input channels, and we found that by adding these channels, we can gradually improve the performance in all 3 matrices. The same as sinusoidal positional encoding. By adding this, will help our model produce better results in all matrices. Here, let's see some qualitative results on stage 2 by taking a closer look at in the top right region. This is the original MR image. The image that follows is the result we gain from applying the synthetic atrophy method. The next 2 images are some 2D results. What we can see here is that by using the synthetic atrophy method, the whole CSF is eroded, and the results are not ideal in 2D scenario. The next 2 images are from 2.5D. Although we can see that there are some slight improvement, but the whole image seems unrealistic. When we apply 3D model, it's getting better. The result becomes even better when we add a positional encoding, which is our proposed method. This image can be as close as the original input, but we can also hold the atrophy region where we synthetic. Let's look a little bit more on the qualitative result for the cortical surface we obtained from FreeSurfer. Applying to the public available VDCRA dataset, we use different colors to separate original surface, atrophy one, and our implanted results. We overlay 3 of them in the last figure, and if we focus on the red circle, the atrophy region, the green line, is wrong because it lies outside of the original gray matter surface, while our implanted image got a robust result, which lies inside. And if we look back to the green line, We also spot wrongly annotated region, which is the orange circle, will not exist in the implanted image. In summary, we successfully built up a robust synthetic atrophy method for better cortical thickness validation, and we hope the method we adapt from 2D to 3D can inspire future research of medical image implanting. And we would like to investigate how to apply our method to other applications like Asian implanting in the future. We greatly thank the support of our grant and ACRE at Vanderbilt, and huge appreciation to our medical lab and VICE. Please follow us on Twitter and GitHub. Lastly, I would like to give my huge congrats to my co-author, Dr. Larson, who just successfully defended her PhD. That's all, thank you.
Thank you for your talk. We have time for some questions. Any question from the audience? No? Okay, so I can ask a question. So at some point, you showed that you use an existing model for doing image segmentation, right? I don't remember the name. So I was wondering, how much does your approach depend on, yeah, this one, the free surfer, indeed. How much does your approach depend on this model and also on the performance of this model? And could you do it also without?
Yeah, great question. So we didn't explore different segmentation methods for this, but we think, we believe that as our atrophy method is based on free surfer to get the surface, that's why we think the free surfer segmentation for the brain tissue is like the most robust segmentation we can currently have.
Okay, thanks.
Yeah, but absolutely we can like apply some other segmentation method to check how the performance looks like in the future work. Yeah.
Okay.
Okay, so we're slightly behind schedule, but let's thank our speaker. Thanks all our speakers.
So at this point, we'll transition to a keynote. So I pull up slides here.
Thank you so much for coming. So today I have the great pleasure of introducing Professor Yamila Yesha, who received her bachelor's degree in computer science and applied mathematics from York University in Toronto, Canada, and her master's degrees and doctoral degree in computer science from The Ohio State University. She then joined the University of Maryland in 1984 as assistant professor in the Department of Electrical Engineering and Computer Science, where she worked until 2017, where she became a distinguished university professor. Recently, in 2021, she moved to the University of Miami, where she is now the Knight Foundation Endowed Chair of Data Science and AI at the Frost Institute for Data Science and Computing. Dr. Yesha is also the director for the Machine Learning and AI program, as well as the Innovation Officer and Head of International Relations. In her innovation role, Dr. Yesha assists faculty in engaging government and industrial partners to collaborate with the university and consults with faculty on developing research ideas into innovations. She was also the founding director of the National Science Foundation Center for Accelerated Real-Time Analytics, CARTA, an NSF industry-funded university cooperative research center that aims to develop long-term partnerships among industry, academia, and government. CARTA partners with multiple universities, including Rutgers, North Carolina State, the University of Maryland, and Tel Aviv University. Over her career, she was awarded more than $45 million in external funding, and her work was recognized by Forbes magazine. She is currently working with leading industrial companies and government agencies on innovative technology in the areas of blockchains, cybersecurity, and big data analytics, with applications to electronic commerce, climate change, and digital healthcare. In particular, she's leading collaborative efforts with the FDA to develop new technologies and approaches for imaging analytics regulation. Dr. Yesha is a fellow of the IBM Center for Advanced Studies. Today, she will talk to us about challenges associated with integrating AI-based solutions into clinical practice. Please help me welcome her.
Good afternoon, everybody. Thank you for the invitation. As I was telling my colleagues who invited me here, this is a miracle beyond biblical proportions because my flights got canceled, delayed multiple times, but we made it. We're here, and I'm delighted to share with you my ideas and the work that is going on at the University of Miami that is primarily kind of grounded in the University of Miami, but we have a number of collaborators that spans national and international kind of collaboration. So without further ado, before we jump into the main topic of today's lecture, I would like to give you the background where the work is conducted and what is the ambition of our study. Clinical flow here perhaps is one of the main things that I want to emphasize. So in our institute, at the Frost Institute of Data Science and Computing, we are working on the problem of national significance that have commercial value. Now, since we are housed inside university, commercial value has the same meaning as it does in industrial kind of setting, means monetization, but it also means some other things like open source software, open source devices that actually enable economic growth and enable many other things like education. So we are looking at this problem, looking at horizontal solutions, and then trying to adopt them and translate them into the real world environments. As a result, we are working with a lot of industrial partners, lots of government agencies, and in a second I'll show you the spread of activities that are going on in the institute and the caliber of the institutions that we managed to collaborate with and produce very significant results. Now, since I'm relatively new to University of Miami, upon my arrivals, I kind of created a vision for the program of AI and machine learning. And this vision kind of concentrated on developing foundational technology tools that are powered by AI and machine learning that have specific applications. And while these tools are horizontal in nature, and there are tons of different vertical applications that can be powered by using this type of methodology and technology, I decided initially to concentrate in digital health, which of course include imaging, and today's talk would be mostly oriented around applications of what we've developed and the research in progress around the imaging technology. But we are looking at the concepts such as software as a device, healthy aging, working very closely with Tel Aviv University there, looking at digital therapeutics, looking at music for dementia, where we are working also with another Frost entity on campus, Frost School of Music, and trying to see how we can use music to either preempt, diagnose, or slow down the development of dementia in individuals. And more recently, jointly with Florida State University and GE and a few other corporations, we started to work on the concept of smart home with health nexus. And why it's relevant here, because we are using a lot of computer vision technology and a lot of technology that is we are applying in imaging world in order to understand how we can actually power your existing homes. And as the healthcare moves away from the hospitals into the clinics and the clinics to the comfort of people's home, how instead of, or in addition, I should say, of smart thermostat and smart devices that we usually already have in our homes, we also have smart devices that would enable us to manage our healthcare needs in terms of prevention, diagnosis, and perhaps to being able to understand and prevent catastrophic events. Now, in any situations, especially in medical imaging, we need to worry about cybersecurity. I usually don't like the concept of cybersecurity. I like the concept of cyber defense nowadays, because you have to be defensive in this environment to understand what exactly is happening. Now, but if you step back, and going back to my original claim that we are looking at horizontal technology, we are actually looking at cyber analytics here, because if you want to apply similar technology or the lowest common denominator to the cyber world, we are actually talking about the analytics tool that powers your cyber analyst to understand whether you actually have penetration, you can anticipate penetration, or you can provide cyber defense tools that would actually enable you to prevent any intervention in the system. So we are working on very interesting concepts that have tremendous application to the healthcare, like zero trust supply chains, trusted execution environment, smart contracts, and more recently, we have a lot of novelties where I'm personally involved in the area of blockchain-powered competitive digital games, and also at the intersection of AI and blockchains, where we have blockchain AI kind of converging technology that powers many medical exchanges and actually enable us to secure a lot of health data. As was already mentioned, I'm a founding director of National Science Foundation Center that spans the entire nation, called CARTA, Center for Accelerated Real-Time Analytics. And there we are looking at the concept where we have accelerated piece. And just 20 minutes ago, we had a discussion where electrical engineering and electrical and computer engineering stops and computer science starts. And I claim it's a continuous flow. And this center is a good representation where we are using accelerated platforms like quantum, neuromorphic, and many other new architectures and hardware devices which powers actually the next generation of analytics. And the data there, of course, is ingested using streaming data. We have smart learning systems and things of that nature. And then we have a number of verticals. And again, center, like the institute, the program that I'm heading, concentrate on cyber analytic and healthcare. Now, notice here, it's not health IT, it's healthcare, because healthcare means different, at least to me, than the health analytics, because it goes way beyond analytics and look at the patient-centric approaches that actually enable us to do all kinds of things. And of course, at the center of all of this is management, triaging, and ability to mine scientific data sets, because whether you have a large archive of imaging, and one thing that probably was not mentioned here, in my career, I had the privilege to be director of large institute set up by National Academy of Sciences at NASA Goddard, where I managed the largest unclassified imaging, space imaging archive in the world. So I always dealt with a lot of images, and then going from space images to medical images, believe it or not, was not a big transformation, except the domain is obviously different. The purpose is different, because here you have a patient, you don't have, let's say, earth science or space science, but then images are images from the computer and digital perspective, and this, of course, empowered me to do these things much easier and more interestingly. Now, this is just some of the members of the center. This center spans 5 universities now, and we have a number of industrial companies that are funding us, and as well as we have about 8 government agencies that are members of the center, paying members. The largest one probably at this point are FDA and Department of Homeland Security that is funding us on a number of very exciting opportunities. And while DHS, Homeland Security, is not so much interested in healthcare, they're funding us on the concept of digital twin technology that is very well applicable in the medical world and also in the imaging world, and I'll touch base on this as well. So just as an overview, and this is, again, just an introduction to the bigger pictures that I want to lay in front of you as a part of my keynote address here, I want to tell you about the opportunities, and I'm sure I'm preaching to the choirs because all of you here are part of the digital world and part of the medical world, where you're trying to take advantage of this amazing power of novel technologies that are emerging and try to see how we can utilize it in the healthcare systems with the idea that, again, we are taking a patient-centric approach where we have patient in the middle of all these activities, and patient is actually our beneficiary at the end of the day. So what we want as a bottom line is to take advantage of AI, radiomics, digital pathology, and all these very related technologies, and I'll kind of try to tie all this novelty from the computer science perspective. And for full disclosure, I'm a computer scientist who also have a joint appointment with the School of Medical School, Department of Radiology. So we want to improve patient outcomes, we want to enhance diagnostic accuracy, and we want to optimize treatment plan. And one thing I'm not mentioning here a lot, but it's kind of implicit here, is that we also want to take care of medical economics. Because if you look at the gross domestic product of our country and where we spend our money, actually we spend more money nowadays on healthcare than we do on defense. And this rate of increase and indulgement, if you will, in this area is unsustainable. So how do we take advantage of this novel technology, not just to improve the patient's health, but also cut the cost where possible and at significance level? And the most important thing here is, as a part of my charter as a director of AI and ML program, is the journey. How do we go from the lab to the market, right? What is this translational research? Because if you go to applied in academic environment, you may be accused by academic colleagues of not being academic enough. And if you go to academic, you may not be too applied or relevant, if you will, to the immediate industry or medical needs. So it's a very kind of fine line where we walk. So we are defining the problems, as I mentioned, of national significance that have commercial value. So first of all, the order of business is to identify the problems that are academically grounded, meaning that they are sophisticated enough, requires the rigor, and have the lasting impact. We are not looking at transient technologies. There are a lot of transient technologies where people actually contributed and making significant profits from, but they're transit technologies. They're not academically grounded problems that are of lasting value, right? So we would like to identify the problems that are really academic in nature, but has the potential to power the practical application at the level where they become part of the clinical flow, part of products that would be licensed or used free of charge as an open source and things like that. Just to give you an example, I've been privileged that at NASA in my institute, the first actually incarnation of Red Hat was developed, right? And it was spun off out of NASA. Now, digital twin technology was developed at NASA, not in my institute, but in a different part of NASA. So government actually creates a lot of technology, and great minds who understand the commercial value of this technology actually come and give it a life in the commercial world. So the objective of today's presentation is to shed a light on challenges of translating AI and radiomics to clinical practice. So we want to understand how we take this enormous technology and make it practical, make it effective in the clinical flow, and make it actually viable in the commercial world of healthcare, so it actually is sustainable and make a lasting impact on the patient's life and on the providers as well. So I'll talk about promising opportunities with these challenges. We'll talk about robust systems, and we'll talk about specific system that is developed now currently and patented at the University of Miami, where we actually are able to triage different AI solutions for clinical care, and we are able actually to work on certain problems like bias and model drift and introduce enhanced security that are the requirements for many of these problems in general. And we will talk about effective implementation of this solution in the healthcare market. So AI is not a magic, and each time I give a keynote speech, I want to put this disclaimer. It's a very powerful technology that has a lot of power and powers many different applications, but it's not a magic. Just to give you an example, I was in Princeton 2 months ago and was giving a keynote at the Consumer Product Conference where we had Johnson & Johnson and Clorox and others, and I had a very powerful business leaders that came to me and said, Yelena, we want you to use AI to solve our problems. And I said, who even told you that this problem needs AI? Perhaps there may be some other solutions because I don't even fully understand the problem. So there is a presumption that AI is some sort of magical toolbox that can address and solve many problems that people have in industry and in any different places. So this is totally not the case. While it's very powerful, what is important is to understand the power, and then once you understand the power, triage your problem so you can actually use the machine learning and predictions and everything that comes with it in the proper fashion so you can really take advantage of this technology and methodology. So here's the real-world examples of AI in action. So first of all, AI in diagnostic world. So you have AI detecting diseases early, diabetes, cancers, and many, many others. They have also prognosis. Now, if you talk to the Institute of Aging at NIH, they even can predict at what months and year you potentially will die based on your sputum. I still don't understand fully the science, to be honest with you, but the technology is advanced even to this level. And of course, personalized or precision medicine, whatever you want to call it, is actually nowadays is a reality. So the question is, how do we get an access to this, and how do we learn from it and understand how to monetize even this type of things, because it's still at the very early stages of adoption and it's not even clear how to monetize these things properly. So we should view AI as something that powers the technology. So many, many years ago with European medical schools, I started a conference on personalized medicine together with also Technion in Israel. And the first conference was, I believe, in Florence in 2010, which was very early in the game. And I had a lot of radiologists and a lot of doctors came to me and said, what do you want? You want to fire us? What is the intent of all this precision medicine? And my answer was, I don't want to fire you. I want to empower you. So when you really analyze the power of this technology, is not to replace medical professionals. It's to empower them at the point of care and bridge the gap that exists nowadays and enable them to see more patients, with a better care and provide them with better diagnosis and better treatment regimens. So the opportunities in healthcare are enormous. And from my perspective, and this is one of the reasons actually I agreed to be on faculty in radiology, because in Maryland I was actually in faculty of surgery. From my vantage point, I see radiology as the perfect place where AI kind of can find its roots, because the training, appreciation, and ability to actually implement AI in clinical flow is enormous. So nowadays, I'm sure that I'm again preaching to the choirs. Many of you are familiar with radiomics, and you know that you can read and diagnose all kinds of diseases using this type of technology. Just to give you an example, we have 3 million TB studies. Department of Homeland Security gave us 3 million chest x-rays that they got from people who crossed the border illegally. It turns out that when people cross the border illegally, they need to give them a chest x-ray to see if they have tuberculosis, because based on the world agreement, if somebody has tuberculosis, you're obliged to treat them, you cannot send them back to the country. So we have this type of ability to read these reports. And what we've done, we use this as an opportunity to actually to automate all these readings and make sure that whatever technology we develop for diagnosis is actually are done perfectly. Now, with the advancement of NLP, we also have a lot of interesting things where we are able to link together EHR and other data and also diagnose the studies. There are very many examples where we use better treatment regimens, diagnosis, and things like that using the machine learning tools. And predictive analytics, and this is the area where I'm very much involved in, is how AI can forecast disease outbreaks, patient deterioration, readmission risk, leading to more proactive kind of healthcare management. So that's another thing that is closer to the public health and closer to kind of medical economics, because here you can understand what is exactly happening in different areas. If you look at today's kind of market share and what is happening, there are about 380 devices, software as a devices that AI powered that are actually approved by FDA. And for the most part, they are so-called standard kind of AI solution. And nowadays, you almost break or classify all the approaches into two classes. One of them being a standard AI, where basically you have an AI that powers clinician at the point of care. I call it integrated AI with a human in the loop, where your human here would be a medical professional. And this is something that we are more or less used to. But more and more, there is an interest from the device manufacturers as well as actually FDA, and we are working closely with FDA, and I'll tell you what we are doing with them. There is a lot of interest in autonomous AI. So in a sense, what we want to have a standalone device that would make decisions without human in the loop, right? And some people saying it's dangerous and maybe unethical because, machines are not human and they can make mistakes. And then the question is where it stops and what if people want to play with these devices. And that's why it goes back to my original point that it's not enough just to create AI-powered and based solution for the healthcare. We also need to create a very robust system that actually support the security and many other things that goes along with these type of things. Now, again, if you look at the value addition or understanding of the value chain, most of the AI tools are nowadays in North America. About 47.6% are actually accounted for the healthcare use in our country, and this is statistics from the last year. And remember, we've been through pandemic, so probably the rate of adoption actually didn't go up, actually went a little bit down. But by the year 2028, the amount goes up to 102.7 billion. It means that it's not a linear, but rather somewhat exponential growth, and it's expected to continue the growth. So what actually prevents, where the problems are, and what prevents actually the expansion of the adoption of this powerful technology in the healthcare and the imaging and many other parts of the different disciplines inside the healthcare. And the prime problem is, to my taste, and I've been in the area for a while, is actually regulations. Right? Of course, there is monetary constraints, there is novelty, you have to make sure that you have the best and things like that. But at the end of the day, it's all about being able to take device to the market and being able to take the right device to the market, because first of all, you need to understand the medical fidelity. You want to make sure that whatever you're using to power the diagnostic treatment regimens or whatever you're doing with this type of AI solution, it does what it's expected to do, does it efficiently, and also it doesn't make any mistakes. And there are a lot of issues that we've discovered while trying to triage the devices that are already on the market and find out a lot of potential issues, and we're able to enable these companies to do what is known market correction, right? So there are a number of companies like Optum and a few others that are adopting these things. And one thing that I would like to mention here, it's not just technology and the devices and the economic investment in all of this, it's also intellectual talent. And being at the university here, it's very clear that without understanding and full appreciation of the power of the technology and having sufficient workforce, it would be impossible to digest or basically implement this type of methodology into the actual clinical care. So there are a lot of, as I said, economic consideration, and some of them would be actually training and consideration of that nature. And there are certain scientific challenges, and this is probably the most interesting part to many of you, especially those that are in research community and students who are looking for great PhD topics, is understanding bias in AI, right? So what is bias in AI and what's impact of the bias? So first of all, we can define bias. You can find several different definitions, but let's go with the easiest one, where you have skewness in the data or the algorithm. So your algorithm is trained on the data that is biased to certain population, let's say. Or you have the algorithm that is trying to optimize certain specific part of the equation or the model and things of that sort. And the other thing that, again, we have now very interesting results in conjunction with FDA scientists is exploring data drift and model drift, okay? Where by data drift, we mean changes in data over time affecting model performance. So as the data changes, as your input changes, and again, if you're doing real time or you're actually doing your AI in the clinical flow, by inputting the drifted information into the system, you're impacting the model, you're impacting the results, and this creates a lot of problems. And then you can have a model drift, of course, which is kind of very difficult to detect and then to manage the drift, where you have changes in the model performance due to evolving data or context. And then you have scientific approaches that address these issues, such as mitigating bias, and this is part of our platform that I mentioned that we built, and I'll be talking a little bit more about it later in today's talk, where we are looking at robust data collection and processing, algorithmic fairness. Then we'll be talking about how to handle data and model drift, where you have continuous monitoring, model updating. And then we have the concept of responsible AI. So this concept is kind of known throughout, and this is what we are concerned about. And then we have a security consideration, making sure that not just we are impose and basically maintain the privacy of the patients, but we also make sure that we have safety of the patients, because if we are controlling the health and life-being and livelihood of individual patients with computers and AI, it's relatively easy to basically to harm or even kill individual without entering the hospitals. And if you don't have sufficient protection and security, we have a problem. Again, this talk is not on security, but just to give you an idea, the healthcare breach is much more expensive than the financial institution breach, which sounds very counterintuitive, but it's about twice as costly for the institutions if they have healthcare data breach versus the financial institution data breach. Okay, so we have a lot of results, and again, I have a talk that probably can last 2 hours. I know we're already 10 minutes, I started 10 minutes later, so I'll give you just a basic overview of what is happening here. We are working on AI bias. We have the modules that we've developed as a part of our platform that I mentioned that we patented that would not just detect the bias, but also mitigate the bias in our data, in our modeling. We are fortunate enough at the University of Miami to be part of AI for Health Disparity NIH $100 million grant and program, which is a national program. Actually, Vanderbilt is part of it. You guys are leading the ethics core, I believe. We are leading the infrastructure core together with Consortium for National Health Disparity. And so we are working closely with some of your faculty on this grant as well. And there are many faculty across the country that are involved in this endeavor. So part of the deliverables that we have there is to understand the bias and specifically how underrepresented population, African American, Spanish, and things like that, are not captured properly in all the assessment and scientific studies, which lead to a wrong methodology, especially if we are creating AI that is applicable to personalized medicine and you're trying to solve a kind of individual problem for a specific patient. And if your models are not trained properly on a proper set, or on a set that's rather biased, we have obviously a problem there. So in a nutshell, if you try to dissect the bias, the type of biases we are working on is data biased and the model biased. And we have a way of detecting both and working on efficient mitigation tools that enable us basically to deal with this type of problems as they appear in the system. I'm moving fast because I'm not even through half of my talk and I'm already late. So how do you mitigate the risk of biasness? So what we do here with diverse and the representation of the data collection. So we want to make sure that the data is collected from the most diverse type of population. I mentioned during our conversation before my talk that we are working a lot with VA data, and it's probably one of the largest databases comprehensive in the world. It has 22 million veterans and things like that. But if you look at the statistics, most of these people are male, right? So you have certain biasness there for the male population, certain age group and things like that. Then we look at the fairness in the algorithm design. And we were finding using diabetes data, for example, that African-American patients, for example, have different regimen treatments in diabetes than primarily white type of individuals. Also, the affluence, the socioeconomic determinants play a significant role here as well. So again, how do you diversify the model and how do you train it on the proper information and with the proper input so your models are actually help you rather than hurt you and produce the right type of results. So if you look at McKinsey & Company, this is not due to us. This is actually something that I took out of the consulting reports. There are six kind of potential ways forward for AI practitioners and business and policy leaders that need to be considered in order to make sure that whatever we are producing is not biased. Because again, biasness can produce wrong results, and sometimes wrong results are worse than having no results or not using AI at all. Just simply use your traditional medicine and basically deal with this. Now, this is another interesting field. So those of you in academia, especially in graduate school, that are looking for biasness, and again, it applies to imagery as well as it applies to anything else, any scientific data set that you're using as an input, is a very good and fruitful area of research moving forward. And there are still quite a few topics available for research and potential prospective PhD dissertation. Now, the other area is how to address data drift and model drift. So what you want to stay current, making sure that the change in time, let's say in statistical property of data, was captured, and each time you train the model, or if you dynamically and continuously train the model, you are training it on the most novel and most recent data sets that are available to you. Now, the impact of drift in AI models in healthcare is huge. Because first of all, what it can do, it can reduce model accuracy and reliability. And believe it or not, this is one of the first things that FDA wants us to look at, data drift. Because they believe that if the algorithms or devices that they'll take to the market are susceptible to a data drift and the model drift, then this is where the biggest problem can occur. And perhaps mitigation of drift is not a simple matter. Because unlike pharmaceutical drugs, when the companies or individuals taking their products to the market, the clinical trials are different. Actually, the devices are on the market after second phase of clinical trials. They're not fully approved, but they're already used in clinical trials sort of on the mass market. And then what is done called field correction, where FDA works with the companies to see if there are complaints or there are some negative or side effects and things of that sort. So one of the biggest problems that they're finding, and we are finding jointly with them, that model drift is very difficult to detect, at least from the beginning, and more difficult to mitigate. So in a sense, you can put device on the market, and you can, if you're lucky enough, early enough to detect the drift, mitigation of the drift is not a simple matter. Sometimes it just requires the whole device being pulled from the market altogether. So that's something interesting. And we are working on the drift management and trying to see how you not just effectively real-time detect the drift, but how do you mitigate the drift so you don't need to pull totally the device, but maybe you can somehow do what they call market corrections in this type of environment. I already mentioned that from my perspective, and I've been around this field for many years, regulatory issue is one of the biggest impediments, okay? So again, I don't view regulatory agencies or FDA or NIST or IEEE, the people who create standards, as an impediment, but in terms of taking to the market, I don't think they really prevent novelties, but they can be a roadblock, if you will, or in some cases, speed bump on the way to actually commercialization of something extremely valuable to the market. And this goes not necessarily because of the bureaucratic process, which is pretty heavy in place, but also because people and even companies, large companies that are going for these regulatory approvals, are not very familiar with the entire work flow cycle. And now we have another curveball, if you will. We have totally new devices that are coming to the market, right? You have software as a device that now flooding the markets. You have 5,000 to 10,000 applications that are coming to FDA, and people at FDA are very smart people, MDs and PhDs, but they are not used to deal with such a big volume, nor they fully appreciate or have the main expertise in this area, because this area is very new. So that's why they're relying on academic institutions and outside experts, like our institute and Vanderbilt and many others, to help them out to understand and develop a robust methodology that enable them to go through this regulatory process and basically be able to sort out which devices should go to the market, which should not go to the market, and what is the unified methodology that they need to apply in order to decide what is good, what is bad, or what needs perhaps a market correction in order to be a viable product on the market. So there is a lot of work that is more, I would say, in the intersection of AI, policy science, regulatory science, standardization that is going on nowadays. And FDI builds large centers like sources, which basically attract individuals with different background in science like us who are doing technology, but also public health, also public policy and things of that sort that work together trying to triage and understand how to come up with this methodology. So what is needed is new guidelines, we need flexibility, speed, and we need the ways where you can improve the fidelity and performance of the devices without actually losing the medical fidelity of these devices. And you need, of course, ensure the safety and fairness and many other good things that usually comes with this type of devices. So we've been doing a lot of drift simulations. So at this point, in terms of drift methodology, kind of mitigations and things of that sort, we don't have yet the fundamental results. So we are still relying a lot on simulation that guide us through the data. And we are looking at different scenarios and trying to understand what happens, why do we encounter sudden performance decay, or why do we have some sort of linear or other incremental drift and things of that nature. There are a number of commercial companies, and I personally, again, I have no relationship to them, but I like what Optelum have nowadays on the market, and there is a lot of interesting work coming out of this company, especially nowadays we are working, again, with you guys at Vanderbilt on lung cancer with Fabian, Dr. Mandavana, and his data sets and things of that sort. So we are looking at lung cancer and breast cancer. And this is, again, the collaboration between our universities and also MedStar, which is a collection of 10 hospitals in Maryland, and FDA. And the next thing, and I just have about 13 minutes left, very briefly, I'll talk about what are we doing in response to the challenges, right? So there are lots of challenges, and challenges come from the scientific technical perspective, because of course we are not at the perfect state of the AI development, the algorithmic development, but also we have other issues that are now coming at us, such as biasness, drift, and regulatory issues that have to do with FDA, because if we are looking at the translational science, not a purely academic kind of scientific results, then obviously we want to make sure that whatever we produce gets into clinical flow. And kudos to my colleagues at Vanderbilt here that managed to have a tremendous system here. And again, we are privileged to work with you guys and take advantage. Okay, so what have we done, and what is our answer, or partial answer, should I say, to all these problems and challenges and opportunities that I've presented so far? So the University of Miami, we've developed evaluation AI testbed. I call it analytics of analytics. So what it does, it powers next generation of AI. So it powers the development and discovery of novelty of AI algorithms, right? Not the application of the existing algorithms, remember. As a fundamental scientist and as fundamental computer scientist, we are interested in advancing the state of the AI versus applying the existing AI. And nothing wrong with applying and applying it effectively, and understanding the domain is extremely important and challenging. But what we are doing here with our platform and testbed, we are creating the ecosystem that we are developing new technologies, novel technologies. We are looking and discovering new risks and opportunities. We are also translating AI/ML technical capabilities to business opportunities. So in a sense, we are working with smaller companies or larger companies that have certain inventions that would like to use our platform. I have an analogy of a racetrack. So if you have a sports car and you want to understand how many miles and what kind of speed limit you can get out of this, usually go to the racetrack, right? So what do you do if you have a novel or new AI algorithm? At this point, to the best of my knowledge, we don't have a racetrack for AI novelty in the algorithm. So the platform that we've developed presents you this opportunity. You can triage it, you can see what works, what doesn't, and where perhaps the challenges are. The other thing we are doing is we are applying experience in operational context to drive innovation. We are taking also the innovation to the clinical flow and trying to understand how it works. And then we are also preparing system for cyber risk associated with adoption, meaning what will happen if we do adopt some novel tool that is AI-based or powered by AI? So what happens? Are we at risk of being attacked or leaked, or are we compromising the safety of the patients? So I invite all of you, if you are interested in this research, to join us. Part of the platform is closed. We patented this technology in terms of secret glue, but some of the modules, it's a very modular kind of platform, are open source. So if you want to play with this, you're more than welcome. Send me an email. I'll put you in touch with some of my faculty there, and they'll be happy to work with you. Ultimately, what we are trying to do here, we want to enable the possibility or opportunity to build trusted and more reliable AI models. And now we are already talking not about single technology. It's not just machine learning. It's machine learning that powered and basically converges with distributed ledger solutions, with certain zero trust solutions. So we are providing solution to the problem versus empowering and moving the needle or state of the art in a single technology. And more interestingly, here we are looking at AI/ML bias assessment and mitigation, and this is the work we are doing with FDA, and we have a large research agreement with Food and Drug Administration, University of Miami with me as a PI, and also Vanderbilt is part of this team as well, where we are working on the novel methodology of assessment of the AI algorithm and looking at their performance. And then, of course, trustworthy AI, where we have secure data, model provenance, sharing using zero trust through permission blockchains, and many other things. So we have publications in this area. Again, if you guys are researching this area or looking for a good PhD topic, this is a very fruitful area. It's just the beginning. Again, this is going beyond the novelty of AI. It's going into methodological assessments and building, as I already mentioned, analytics of analytics. So here's kind of a very high-level architecture of our test bed. We have applications where we have healthcare, of course, EHR, radiology, IoT devices. Here primarily we mean medical devices, digital health, other applications. Then we have modules, process evaluation, bias assessment, and many other modules. We have about 30-some modules that are part of the system, and it's keep growing. And then we are fortunate at our university, at the University of Miami, to have a very powerful supercomputer. And this is part of our so-called accelerated platform. So it's called Triton. In a second, I'll show you later the picture. And then and we are putting and basically implementing and triaging our platform on this system. We have a lot of work on the converging technologies as it applies to the healthcare. We have what we call privacy-preserving production and support of federated learning, because most of the time, the information, the medical data sits in different medical centers, and you need really to collect it or basically fuse it and create a single stream and make sure that, first of all, you can do it close to real or in real time, but also you want to make sure that you don't lose any fidelity of data and there is no foul play in this type of environment. So this is Triton. This is our supercomputer in our institute, and we have a pretty significant advanced computing system, and that doing accelerated training and evaluation of very large AI models. And we have other smaller clusters that we are taking advantage of. We also have visualization laboratory that help us to visualize things, and we also have a wide area network that all these devices are actually interconnected on. So we have a number of ways to evaluate the model. Again, I would not go into details. I just have 5 minutes left, but Basically does a lot of things in assessment. If you have an interest, I'll be happy to share with you the papers and some white papers that we wrote on this and what we have so far and where the world is moving in terms of next generation of the platforms and what we believe is missing from the platform. And we would like to invite you guys to join this effort and see how you can contribute. Now I have a video here that I don't have time to play. But again, we'll put it on the web if you're interested to look at actual technology and how this platform works. We have a detailed kind of description of all of this. It's a very short 10 minutes audio kind of description of what is part of our platform. Now, we work with a lot of companies, as you saw. I just want to give you a very fast example here. We have worked with Red Hat International. I don't know if you know them. These are people who are using radiology to assist very poor countries. This is non-profit consortia started by radiologists who spent part or most of his career at NIH. And nowadays, he has devices in 88 countries, primarily African countries. He goes to low-resource, under-resourced places, and it turns out that in these places, what is happening, the problem is not even having the device, but the problem is to have radiologists to read the report. So it occurred to him that if he gets enough donations, and this is funded by Google Foundation, Bill Gates Foundation, so there are resources that are flowing in, but the question, how do you take advantage of this technology at the scale of a country, let's say? And one way he is doing it, and specifically looking at tuberculosis, because this is kind of a prevalent, unfortunately, disease in these low-resource countries, and in African countries, is to send the devices and then use the computer-aided technology to read the reports, right? And then maybe have a radiologist sometimes look at the reports, and in certain cases it's a clear cut. Either the person has TB or doesn't have TB. And since there is a World Treaty to eradicate tuberculosis around the world, there are also World Health Organization resources and things of that nature that are happening. So Red Hat is a member of the NSF Center that I've created, and we also jointly got significant funding from Google Foundation to work on this methodology where we are using computer-aided diagnostic tools to detect tuberculosis. Now, but however, what is interesting is that there is significant kind of domain shift in tuberculosis screening, and we apply kind of the same type of unsupervised kind of domain adaptation screening for different countries, like Montgomery County, which is affluent county near Washington, D.C., then China and India. And it turns out very interesting result, which is very kind of intuitive, that the poor performance found when train AI models using one population and test on others, meaning you train your AI model, let's say, on population in, I don't know, in China, and then you apply it to population in Washington, D.C., and we have a problem. So what it means? It means that you have a data drift, you have biasness, and you really need to make sure that you are training your system and applying them to the very kind of similar kind of data sets. Now, two combinations, what we've discovered, lead the best results, superior results, where you have US, China, and India and China, okay? So this is where we found the best type of outcomes by applying the AI tools for diagnostics. And the board-certified radiologists observed that many cases in China data set exhibit more severe disease presentations than others. So again, depending where you go, which country, and things like that, perhaps the diagnostics done at the level where disease progressed way further than in the other countries. So it's exactly 3 o'clock. Thank you so much. I made it a very high-level presentation. I'm sure that you guys have a lot of technical questions, so I'm here to answer them.
So please come up to the microphones for questions. I see some people coming. What?
Hi. Thanks for the great talk. So I am currently a medical student, and I had this question in my head where, you know, with the shift toward AI and shift toward all these data-driven things, and when we bring it to the clinic, how would you, as an expert, sort of get patients on board with this shift that's happening with, given all of the cultural, you know, sort of stigmas associated with AI and these catastrophic failures, like self-driving cars failing and all this stuff, when it comes to counseling a patient for their health, how would you sort of get them on board with this shift?
Well, actually, it's a very good question. In fact, for all full disclosure, as you realize, I'm a PhD in computer science. I don't have MD, although I'm a faculty in radiology. So it is a cultural shift. What I found among the patients, and I do have a privilege to sit with doctors who are talking to the patients and advising them and things like that. There are certain patients that know as much as the doctor because they go and read. There are certain patients that are afraid of AI. And there are certain patients that's kind of on the fence because they think it may be good for me, but I'm not sure. So I think what is needed is education. And education starts not from the patient. Education starts, I guess, from people like yourself, from the doctors and future doctors that comes from the medical school, which endorse this type of methodology. It's sort of like using the mobile phone, using the ATM machine. When the ATM machine came into existence, people were afraid that if they use it, then they'll lose their money. So the same thing comes here. They're saying, I'm going to steal my information. What if the machine goes wrong? What if somebody is trying to play with my X-rays and things like that? And I give you an interesting example. We actually were paid to do an interesting development or novelty. It turns out that if somebody has a car accident and you have, let's say, deformation of the face, and you go to a dentist or to the surgeon to reconstruct the face, if you take enough X-ray images of the face, you can reconstruct the face. So in a sense, we're all signing that we protect the privacy of the patient. But if you take enough X-rays, and imagine you have CEO or some major politician in a car accident, you take enough pictures, you already know the identity of the person. So we created an overlay, kind of mask on the face that does not impact the medical fidelity, but would impact the reconstruction process of the actual face of the individual. So, but to answer your question, this is just an example directly, I think it's education, it's culture, and it's also a situation where a patient would appreciate the power of this technology and what it can do for me as a patient. If the patient would see that by utilizing and applying this technology to my case, I get the better outcome, they'll come running, they will not doubt the technology. That's my opinion.
Thank you.
Sure.
Great talk.
Thank you.
I thought it was really interesting how you were talking about the future is going to be moving towards these AI systems not having humans in the loop.
Right.
And thinking on that topic, when we do academic research, what are your thoughts on the kind of pros and cons of chasing absolute model performance versus model explainability?
Well, I think autonomous AI is here. So it's not something, and of course it's evolving and getting better and better. Now, from the academic perspective, all of us looking at the better lower bound, it's better constant, better this, better that. So if you look in the medical world, and this is my personal view, of course, is that from my perspective, it's better to have a novel device faster to the market. If it's, let's say, 99% bulletproof, especially for diseases like terminal cancers and things like that, some incurable diseases, then wait and perfect it perfectly. That's why FDA decided to take devices to the market much faster, any devices, not just AI devices, than to take, let's say, pills to the market or pharmaceutical to the market. Because then they can look at the market and see how the patients react to this implant, let's say, whether it's heart implant or, I don't know, hip implant. And then if it's really terrible, then they'll take it off the market. But for the most part, they do market correction. So my intuition would be, as soon as we can take some novelty that proven fidelity in clinical trials, to the market, the better off the patients are. Because if you remember, when I started my talk, I said we are taking patient-centric approach. At least I take patient-centric approach as a part of my research. So first of all, at the nuclear of my research is the patient. So unless patient benefit first, the next consideration, the secondary, like economic consideration and government consideration, because many people are paid by Medicare and Medicaid. Obviously, they spend a lot of money, they can save a lot of money. But this is consideration. I'm not dismissing it, but this is not the prime consideration that I think us as academicians should think about it. We should worry about the patient's health.
Thank you.
Sure.
Hello. Thank you so much for the high-level talk. So I also have a high-level question. So how do you see foundation models playing out in healthcare, and where, in what way do you see them working?
How do you define foundation model? You see, foundation model in exact sciences mean different things what it means in medicine, because I personally don't view medicine as an exact science. I view medicine as an art that is powered by science, because many times the best doctors I met in my life are actually people who are saying, I have to look at the patient. He said, sometimes the lab results may be perfect, but I look at the patient and see something is wrong. So it's the experience and the art of practicing medicine that is important. While in physics and mathematics, we are used to exact foundational model that give you the precise answers.
Yes, well, I meant more like, I mean, there's this trend in like machine learning community where basically you have a large model that basically can then be used for many downstream tasks. So for example, you have a model that kind of understands X-ray images, and then you can use it for many downstream tasks, so like X-ray diagnosis, prognosis, and so on. So, for example, do you see a role in which we can have like disease-centered models or maybe organ-centered models like this?
We do already, right? So,
and
but
how is that going to work with personalized medicine?
Well, I actually am very fascinated with more molecular level, with more like theranostic modeling, because we have a very prominent cardiologist that we just hired at and he's looking at the kind of creating digital twin of stents for the heart, right? And I said, why don't we model like a digital twin of individual? Because I think you really need to have holistic view of the person in order to understand things, but this is very difficult, although technology now is developing and things like that. So to answer your question, yes, for specific diseases, we are practicing this, and they're very well-established models. But let me give you another example from my personal experience. It was about 12 years ago. The head of pathology from George Washington University walked into my office at the University of Maryland. And he said, Yelena, you have to help me. I said, you know, I don't like blood, but I definitely don't like to deal with dead people, right? So he said, no, you don't understand. What is happening is what I found out in my practice. I have 2 women with breast cancer. One has stage 2 cancer, one has stage 1. Same treatment regimen based on the medical profile and how they should be treated. Stage 2 lives 5 years, cancer-free. Stage 1 dies after 6 months. What happened? So, and this is where I realize that its immune system, it's not just breast cancer. It's the immune system of the body and the entire state, the holistic view of the patient, what I call. And then when I told him about that, then we built the models, and I had a couple of students who did PhD dissertation. We used Monte Carlo. At that time, it was not even AI. It was pre-AI kind of thing that we are trying to predict and anticipate the survival rate. We were trying to match the treatment regimens to the survivability, meaning longevity of the lifespan versus the quality of life and everything else. So this was the kind of the optimization we were looking at. But why this example is relevant? Because nowadays you can model specific disease, breast cancer, prostate cancer, you name it, right? Or use radiology reports, since it's medical imaging kind of conference here, and the images actually everywhere, so definitely in an oncological space. But at the same time, we don't have models yet that model the entire individual. And that's why mathematically, if you really want to think of medicine not as an art, but as an exact science, I think isolating the problem is not always the best type of way of solving the problem. So that's where I am. I mean, I don't have the complete answer, but I feel that it's probably we are far from reaching this type of point. But if we do reach, then there will be another problem that I want you guys to think about that many people believe in, called singularity. Because if we are able to model the entire human and have digital twin of individuals, then perspective of us living 140, 150 years goes up exponentially, and then become economical and ethical question whether the society can sustain so many individual nerves and who is going to maintain them and things like that, which has nothing to do with computer science directly, but more of economics and the societal kind of situations. But I think singularity eventually will come, but I don't know when. And unfortunately, I don't believe it will be in my lifetime, but because I've been through electronic commerce, I've been through a lot of revolutions, internet and digital library. I was in the government at that time and was in charge from NASA perspective on all these things. People saying, there'll be no libraries. And I was just walking, actually my husband was there with me at the University of Miami, and guess what? 30 years later, these libraries are very vibrant and they're alive. And 95, 96, people were saying, that's it, this is the death of digital library. When I started to work on electronic commerce, they were saying there will be no currency. It will be electronic currency, and OECD and all the commerce department were freaking out, saying that there will be too much money in circulation because people will produce digital currency. So you name it. So let's work on what we call theranostic digital twins. Let's try to create digital twins of humans, and then I think we'll be in a good shape from the health perspective.
We have time for one question left, given flights. So this actually kind of answered my question. I wanted to ask about this idea of multimodal training and how to replicate the success of GPT in the medical world, and specifically in radiology.
Well, ChatGPT, again, is a very interesting technology, but if you look inside, and I've been interviewed by a number of papers in Miami, and they're saying, oh, ChatGPT, there will be no need for professor, the same kind of attitude. And we should embrace this technology, but it has a lot of flaws. And us as a scientists, as medical professionals, we need to understand what it can do and what it cannot do, right? And sometimes to know what it cannot do is more important than to know what it can do for you, right? Because certain things you can do yourself. So it does a lot of exciting things, but it cannot do critical thinking, right? So when you come to a specialist in certain area, I don't know, orthopedic surgeon, or I don't know, a radiologist, and things like that, you have a domain expert. And this individual has critical thinking. ChatGPT doesn't have it, right? Not yet, at least. So the state of the art of the development of this technology is still at the level that we cannot adopt it in substitution of human. So I would embrace this technology. And definitely, as I said many years ago, it's not going to replace radiologists. It's going to empower. They'll be reading more reports, and they'll be reading them better. And those of you who are in School of Radiology, there is a very kind of mind-boggling statistics that really bothers me as prospective patients, that 32% of all radiology reports are actually read incorrectly by individual radiologists. So this is where actually this technology can really make a dent and help radiologists to be better radiologists, but it's definitely not replacing humans.
Thank you.
My pleasure. And thank you again for inviting me, and next time I promise to come for a longer period. Thank you.
And with that, I'll close this session and invite people to go to the posters. This is the even session number. So 2 through 30 and 32 through 60. Thank you.
race is?
I think this is the time when we said these. We said 3:15 was the get in the car time. I think we nailed it. When I was choosing the airport when I commuted to Baltimore, I went in
it's for tomorrow.
It's for tomorrow.
Will we see the presentation names on this screen, or?
Yes.
Okay.
You'll see all the slides as well.
Okay. So we'll know what we're introducing. Ooh, it's bright. Daniel says to not forget to introduce ourselves. This is what I've learned.
Okay. See if I got an email about it. What was the name that you uploaded?
Oh, that does work.
Yeah, at some point.
I think it's pretty good at not picking up. Or not. It's fine. It's fine. Whatever. That'd be great. What could go wrong?
It was on the internet. Okay.
Yeah. Like I said, I'm not usually used to the spotlight being on the session chair. Isn't the speaker the person that's important?
But even for the speakers, I think it's out of line.
No. Can't see the audience.
I'm gonna check on my other computer.
Oh no, under technical difficulties.
That's fine.
Yeah, also get something to drink.
Yeah. So you'll. Oh, minute. Sorry, I have to reset up again now. Just let me check the order here. Just to make sure.
I think I know it.
Okay.
I think the one with nerve is the second one.
Okay, hello everyone. So welcome to the last session of the day, which is gonna be in synthesis. I'm Jose Dols, I'm from E2S Montreal.
And I'm Jian Wu, I'm from Vanderbilt University.
So let's welcome to the first speaker. It's Gianni G. That is gonna present her work on CP2 image generation, high quality single cell images using cell profiler representations. Please go ahead.
Yeah. Hello, everyone. My name is Yanni, and I'm from University of Glasgow, and I'm really going to give a talk about my research work, that is CP2 image, generating high-quality single-cell images using the cell profiler representations. First, let me introduce some background. With the development of microscopy imaging, a large number of cell morphology images has been generated efficiently, which contains rich biological morphology information. To identify and quantify this cell morphology, and people generally do like phenotypic profiling, that is to extract the representations of the cells, and so that the similarity between the representations, that is, could reflect the similarity between the cells. It could not only identify the phenotype, it could also like capture the subtle features. Generally, there are two main methods for measurement in the microscopy single-cell images. The first one is the traditional handcrafted method, that is, we call it as, we take the example of the cell profiler. Cell profiler is a cell image analysis software, and once we feed the images into the cell profiler, we could generate the cell profiler representation matrix. Here is an example of the cell profiler representation matrix, and we could see that every column that it could describe a property of the cells. For example, like the cell area shape, cell intensity, and something like that. We call this kind of representation interpretable. Another method is that the machine learning method. If we take the VAE, variational autoencoder, as an example, that we regard the sample latent vector as a representation. And we know that the VAE representation could generate images, but it's not that interpretable because we have no idea how each dimension of this VAE representation represents. So now the VAE representation can generate images, but it's not very interpretable. And the cell profiler representations are interpretable, but has not shown the generative ability. So we come up with a problem that can cell profiler representations generate realistic images. To solve this problem, we propose a CPU2 image model. Because we are starting from the very limited information that the cell profiler representations have already thrown out much of the information in the image, so that generating a realistic image purely from the cell profiler representation is a very challenging task. So first, we would like to see if it is possible. Here we have a generator G first, and then we try to feed the cell profiler representations into the generator, and then we generate images. From the generated images, we see that it is possible. So, but the generated images is not very realistic. So to enhance the generation performance, we add a discriminator D here. Come along with the discriminator D, that we also have like two loss functions. The first one is that the MSC loss set of the hidden representation of the original images and generated images. The other one is the cross entropy loss that is to train the discriminator. The data set we're using is BBC 21 data set, that is human breast cancer cells that are cultured in the wells, and each well is treated with a compounded concentration. We also call that as a treatment. The image under a treatment are evaluated for a cellular response, and the treatment with distinct mechanism of action can represent phenotypic cell effects. And the MOA here, that is a label of the data set. Here's an example of how the data set looks like. It has three channels, the DNA, tubulin, and actin. Once you merge it into the RGB, and it's an example of the image. In our experiment, we have two phases. The first one is the training phases. That's once we have obtained the data set, we segment this to a single cell data set, and then we generate the cell profiler representations of the single cell images. And then we feed both the generated images of the segmented single cell images and the cell profiler representations of these single images to train the CP2 image model. In the testing phase, that we only use the single cell profiler representation feed into the cell profiler CP2 image model and then generate images. And this is our point. To explore the quality of the generated images, just like the standard generative study, we compare the generated images from like the CP2 image model with other models, and we also like quantitatively measure the generation performance by using the FID. And if you look at the images, we could see that the CP2 image model has the generated images from the CP2 image model has already captured the cell features. Since that our model starts only from the cell profiler representations, it's a very challenging task. So our point is not to try to like have a better generation performance than other model, but we just would like to know that our model has already captured some cell features, cell morphology information. And if we look at the FID here, the FID score of the CP2 image model, that is 68. That is, even though it is a little bit higher than the VA Plus and LSCAN, but since we are very like hard task, so it is not very far away from these two other models. And we still think that is okay. We are satisfied with that result. And there is a specific way that we can assess the quality of the generated images of the CP2 image model, and that is to measure the generated images with the CP pipeline and correlate them with the original CP representations. Because our model starts from the CP representations, and once we obtain the generated images and we feed the generated images into a cell profiler software again, and we could obtain the corresponding cell profiler representations. And then we try to do a pairwise correlation between the cell profiler representation of the generated images and the original images. This could help us to track down how the generative images capture every single CP features. Ideally, if they capture all of them, that is very perfect. But in our case, they have already captured a large number of the CP features. If, for example, the plot A is a sorted correlation coefficient, and if you look in the top of this plot A, and we could see that some CP features has already have correlation coefficient higher than 0.8. And the plot B is a scatter plot of the 6 dimensions with highest correlation coefficient value. And we could see that most of them are about nuclear area shape or nuclear orientation. So now here we would like to explore how single dimension affect the generated images. We try to manipulate a single dimension in the CP representations and increase the value of its feature gradually and fix all other dimensions. We choose two CP features, and first one is the nuclear area shape orientation. That is measures the angle of the x-axis between the angle between the x-axis and the major axis of the nuclear ellipse. So when we try to increase the value of it, we could expect that we have a clockwise variation of the generated nuclei. And here's our generated images. We could see that the generated images has this kind of variation. We also take a look at the nuclear area-shape area, that is to measure the nuclear size. Once we increase this CP feature, that we could see that there's, in the generated images, the nuclei gradually increase. This is also very interesting. So next, we would like to know if we could do a more biological, meaningful interpolation. So we think of to explore if the CPU image can generate cellular phenotypes that are associated with certain conditions. First, we took a look at the MOA, that is the mechanism of action, that the cell responds to that kind of treatment. A previous study has already told us that cell profiler representations are predictive of MOA. That means the changes of the cell profiler representations corresponds to the changes of MOA. So we do interpolation in the cell profiler representations from the negative control, that is the most left column here, to the target cell, that is most right column, that under different MOAs. And every row that it represents different MOA, and from left to right, we could see, for example, if you take a look at the first row, that from left to right, that is from negative control to actin disruptors. In this generated images, we could see that the actin, that is the green channel here, that fall apart and condense into like little blebs in the edge of the cell. And that is exactly what the actin disruptors do. And for the second row, that from left to right, we could see that the DNA starts to fall apart, and that's also what exactly the arula kinase inhibitors do. We also took a look at the compound concentration. First, we look at the association between the CP features and the concentration. The plot A is a PCA plot. The PCA space is a reduction of the cell profiler features. We could see that there are like three clusters for the concentration. Light blue, the negative control. The blue one is the concentration 1 UM. And the dark blue is the concentration 3 UM. And we could show that, and this shows that the changes in the cell profiler corresponds to the changes of the concentration. So we see like a path from the negative control to high concentrations. So we did a like linear trajectory from the negative control, the low concentration to high concentration, and generate images about on that. And plot B, the second row that shows the generated images on that. So from left to right is from from low concentration to high concentration, and we could see that the green channel gradually disappear, and that corresponds to the MOA of this compound that is also like the actin disruptor. So that is also what we expect. So in conclusion, that we have shown that CP2 model can directly generate high-quality cell images from the cell profiler representations, and the most biological information is well preserved in the generated images via the CP2 image, and the CP2 image can generate conditional phenotypes without separating training with extra labels. And sometimes it could also like generate very uncommon phenotypes. Thanks very much. Many thanks to my supervisors, Kay, Bill, and Mary. Thank you.
Thanks. So now we have time for questions. Okay, I might have a question. Which is the goal of generating all these images? Actually, which is the goal? I mean, you have these images, you generate new samples.
Yeah.
What do you want to do with them?
We could like first increase the data set, and we could like generate like a very common phenotypes on that, and we also like could generate the image to perturb the existing like CP representations and generate the images we want. And they would also like help some researchers like give them like intuitive way to visualize the images.
But for example, one question I have from my experience is that when you work with these fake or synthesized images,
yeah,
I know typically doctors, they have some, I mean, they have some word on that. Sometimes they don't trust all these images. They might have some problems with that. So you find this experience in your work?
But it's just help them to like visualize. Sometimes if we only have the mean of the self-profiler representations, and we would like to have a visualize how the like rough the images look like. Then you could use this CPU2 image model.
Okay. Okay. Thanks.
Thank you.
Okay. We have a question there.
Yeah. Did you do any feature selections for the CP features? Are you using all 1500 dimension features, or did you do any feature selection?
I only used like 400. Yeah, just about 500 dimensions of them.
Okay. Thank you.
Thank you.
Could you explain again what is the conditional phenotypes here in the third bullet point that you? Yeah.
This one, the conditional phenotype is that it's not condition. It's not an interpolation. It's also like an interpolation of the like a cell profiler representation, but it could generate the condition. For example, here's like condition on the concentration that. The light blue one is like negative control. That means that it's a very low concentration, and dark blue is like very high concentration. And if you do the interpolation in the cell profiler representations, we could like condition on this different kinds of different concentrations. That is a conditional phenotype.
Okay, maybe one last question.
Hi, thanks for the presentation.
Thank you.
Maybe I didn't understand. So when you want to generate these conditional phenotypes,
yeah,
you can do that just straight with the model that you've trained.
Yeah.
It doesn't require any sort of additional cell profiler vectors.
No.
No, so you can just generate that straight away. Yeah.
Yeah.
Okay. Yeah, I think that's all I want to ask. Thank you very much.
Thank you.
Let's thank again the speaker.
Yeah. Great. So now we'll go on to our second talk of the session. We'll hear about ultra-nerve neuroradiance fields for ultrasound imaging. Please take it away.
Hi, good afternoon. It's a great pleasure to present here today. My name is Magdalena Wysocki. I'm a master's student at the Technical University of Munich. And on behalf of my collaborators, I would like to present our recent research paper titled Ultra-nerve neuroradiance fields for ultrasound imaging. This work originates from our research at the Department of Computer-Aided Medical Procedures and Augmented Reality. Before I go into method, I would like to first present the motivation behind our research. So ultrasound in general is very relevant in clinical practice, not only because of these real-time imaging capabilities, but also it has important aspects in comparison to other methods like magnetic resonance imaging or computed tomography. It is safe, both for the patient and clinician. It is cost-effective, and also, especially with recent development in portable handheld systems, ultrasound can be performed virtually anywhere. However, with 2D ultrasound, we do not have important spatial understanding of the scanned anatomy. This, in fact, increases complexity of both acquisition but also diagnosis. And for the acquisition, we rely on the hand-eye coordination. And therefore, it limits availability of the ultrasound because now clinicians need to be both trained in the sonography but also in anatomy. And this problem is traditionally addressed by 3D ultrasound that provides us volumetric representation of a scanned anatomy and also increases our understanding. However, 3D ultrasound has its own limitations, and in context of our research, we are referring to limitations of the 3D reconstruction process. And in particular, we will be looking at the anisotropy of B-mode ultrasound. And by anisotropy of B-mode ultrasound, I'm referring to the fact that B-mode images do not only depend on the scanned anatomy, but also directly on the position of the probe, so position and orientation. This is illustrated here. So if you have different positions of your probe and, for instance, very reflective structure in your anatomy, acoustic shadow direction will be different in between the images. And once you try to do a composition of these multiple views, you end up with some sort of average over these multiple views. This is a problem because we are losing very important view-dependent details. And moreover, this process is irreversible, meaning that we cannot render B-mode images exactly as if they would have been observed by ultrasound device. Therefore, the goal of our research is to provide a 3D volumetric representation that offers these rendering capabilities so that we can render images exactly as observed by ultrasound device. You haven't seen this. But and once we have this rendering, we can then render cross-sectional planes that may have been missed during acquisition, but they are important for the diagnosis or the navigation. This increases flexibility of acquisition protocol, and also we can, with these renderings, we can then enhance other automatic processing of ultrasound. So I've been talking already on neural radiance fields, but I haven't introduced it yet. Let's take a look what the method is about. So in computer vision, this problem of view-dependent rendering has been recently successfully addressed by neural radiance field. And this is a method that allows us to render photorealistic seamless views. The example of these views are presented in this graphic. But let me walk you through the method, how it works. So this method consists of two components. The first component is neural network, and this neural network learns from the unstructured set of images for which camera poses are known. And once we have camera poses, we can compute position and orientation of each sampled point within the volume. So you can imagine that this network is a volumetric continuous function of your 3D space. And this allows us to map this position of the sample point into color and density information for that point. And once we have this information for many points in our space, we can then use volumetric rendering, which in case of NERF, it's integral over all rays, over all points belonging to the ray that starts in your pixel position and then traverses into space to end up with the rendering of the color information in your image space for this particular novel view. In UltraNerf, we are taking very similar two-step approach. In the first step, we define rays for each scan line in our B-mode images. Then we can sample points along this ray that could be defined by 3D Cartesian coordinates. And then we train a network to be a function that maps these Cartesian coordinates to set of rendering parameters. This set of rendering, this vector of rendering parameters for this particular point, in our case, correspond to physical properties of tissue, namely attenuation, reflection, scattering density, scattering amplitude, and the probability whether the point belongs to the tissue interface or not. Then we are using volumetric rendering function, which I will talk about in next slide, to render final B-mode intensities, exactly as observed by ultrasound device. So Rafael was talking today about physics of ultrasound, but a wave physics of ultrasound. In our volumetric rendering, we are using a ray-based model of ultrasound. This model is known in the ultrasound simulators, so it's been already used there. And this consists of two factors. So one It's responsible for the reflections, and the second one for backscattering process. Both of them, for the current position within your on your ray, for your ray head, depend on the previous previous points on the ray, and this is defined by the transmission function. This transmission function tells you how much energy of your acoustic wave has been lost during the propagation through the tissue. And this is defined by the previous reflections and previous attenuation. So now, for the current point, we have a reflection coefficient, and we know how much energy of our wave we have. But for backscattering, we need to look into other model. Backscattering is defined by the scattering map, which is a probabilistic model parameterized by the scattering density and scattering probability. Before we take a look at the results of our renderings, I want to mention the data set that we've been using. We have acquired B-mode images in a form of B-mode sweeps, for which we have pose annotations. For the real B-mode images, we have robotic tracking. So we have simulated B-mode images of liver and the real B-mode images of lumbar spine phantom. The unique aspect of our data set is that we have multiple observations of the same region of interest. How do we achieve this? We have a constant trajectory, and we tilt the probe by 10 to 5 degrees in between the sweeps. So we make sure that each of our sweep looks at the region of interest from different viewing observation angle. So now let's take a look at the results of our rendering. We compared the results to one traditional method and one method I will explain right now. So from left to right, we see ground truth data. The compounding here refers to the reslicing from compounded volume. For that, we take our training sweeps, we compound the volume, and then reslice. And no rendering, it means that we are training the network to map Cartesian coordinates to intensities directly, so we are not using any rendering function. Then it's a simple, implicit neural representation. Important here is that without rendering, we are not able to consistently represent shadows because we have no directional information about the physical phenomena. And with rendering, our shadows are consistent with expectation. Similar, it's on our phantom data. So this region that is marked here should be occluded by the spinous process. It's part of lamina. And you can see that without rendering, we can observe intensities in this region, which may not be visible in the 2D projections, but we will look into 3D. So just so you know what you are looking at, we'll be looking at the sweep compounded from the volume acquired from this direction as presented here. And in this case, spinous process casts a shadow over lamina, so this is not visible. And we can see here that from our compoundings that intensities without rendering of the lamina are included in B-mode images, but with using physics-inspired rendering, we can properly reconstruct this physical directional phenomena of acoustic shadow. To conclude, we presented a proof of concept for neural dense fields for ultrasound. In our work, we address volumetric rendering in line with physics of ultrasound. And this enables view-dependent synthesis of B-mode images for a static scene. So for the future work, you could think about deformations which are not included in this model. Thank you for your attention. I'm open to the question now.
Thank you so much for the presentation, very insightful. So I'm going to repeat the question that I asked you earlier. Since this is a proof of concept system, I'm wondering what are your future steps to basically improve this, pipeline, this framework?
You could look into many directions. First of all, we are looking at the ray-based model. You could think about the 3D representation for your beam, right? That's one thing. But also looking into deformation. So this cannot be used in the real clinical context because we cannot avoid deformation. So first step would be include deformations in this model.
Mm-hmm. Thank you. So as far as deformations and those things are concerned, you would probably do motion studies and actually capture clinical data from patients, hopefully, right?
Mm-hmm.
All right, perfect. Thank you. Looking forward to your future papers.
Thank you.
This was so cool. Thank you so much for the talk. The idea seems so cool, and it feels like it could be general. Do you think that was specific to the rays that happen in ultrasound, or do you visualize that this could also happen in other sort of imaging problems where you can't see everything?
I encourage you to look at this as a regression problem and look at different models for different modalities and adapt this method for different data types, right? This is nothing ultrasound specific. I wanted to show that it's nothing natural images specific, right? You can try to look in neural fields in different modalities.
Okay, great. Thank you very much.
Oh, I had a question. So you have more degrees of freedom with the ultrasound, right? You can set a lot of different settings, and compared to cameras, which just have X, Y, and Z. How do you know when you've collected enough data? Since in the dinosaur head example, you could see on the edges of the image, they were less well reconstructed than in the middle where there was more data. Can you detect that kind of insufficient data in the ultrasound?
This would be next step, right? Because our data set is very dense. We had robotic tracking, so we also make sure that this is dense representation of the scene. But probably you would need to, you will go into direction of interpolations if you don't have a representation for this region, right? So I would like to see also a work on how many images do we need to represent the structure properly? Right? You could also think about the geometrical priors or anatomical priors for your methods, and then think about, okay, how many images I need if I have this prior information.
That's cool. It would be fun to incorporate some priors. There are no other questions. We can
Thank you.
Thank our speaker again.
Okay, let's welcome the last speaker of this session, Vivek. Let me try. Narayanaswamy. Sorry.
You got it right.
Okay, sorry for that. Anyway, so welcome. Go ahead, please.
Hi. Good evening, everyone. Welcome to my presentation. I'm Vivek Narayanaswamy from Lawrence Livermore National Labs, and today I'll be presenting our work, Know Your Space, Inlier and Outlier Construction for Calibrating Medical OD Detectors, and this work is in collaboration with researchers from Microsoft and Arizona State University. When medical imaging AI models are deployed in the open world, there's always a chance that they are exposed to a variety of open set examples with diverse semantic characteristics with respect to the training data. So when I talk about open set, they are data that you can draw from the wild, and you can think about them being in two distinct groups. For example, in case of modality shifts, as you can see on the image on the right, they contain images that are drawn from distinct and disparate imaging modalities and acquisition protocols when compared to that of the in distribution. And in this case, it is a skin lesion. And second, the open set data could also belong to what is called novel classes, which contain images that are completely unseen during training. And these images share a lot of semantic similarity with respect to the in distribution. And this is one where your model needs to confidently reject. So In order to support the safe and reliable adoption of AI tools and to foster its adoption in practice, it is not only important that they work well on in-distribution data, but they also are capable to effectively reject these types of open set data. And consequently, there has been a lot of focus in the vision community to develop what is called model scores in order to exactly categorize between the in-distribution and out-of-distribution data. So among a plethora of scoring functions, one such popular approach is what we call generalized ODIN, which constructs a detection score by decomposing model confidence without the use of any out-of-distribution trained data a priori. And it has been shown that it works really well on natural images, as you can see in one of the histograms here. So the solution is simple, right? We can easily adopt such off-the-shelf detectors and use them on medical imaging data. But wait, here is the catch. So despite these OD detectors or these classifiers achieving high accuracies on the test data, we find that the conventional OD detectors struggle in case of medical imaging, and especially the open set conditions. So the graphic here gives a few examples of the modality shift as well as the novel class detection that we consider in this paper. And the train and test that is marked on these images correspond to the in-distribution data as well as the out-distribution data respectively. And we compare the rejection performance using the AU-ROC scores. So what can be done? So a potential fix in order to ensure that the OD detectors are sensitive enough to detect such open set data is to calibrate them in practice. By calibration, what I mean is this is a process of, in fact, doctoring or informing the classifier during training the regimes of data to which it needs to generalize to and to regimes that it must not. So the process of calibration, in fact, can be given by this objective function here, and this is incorporated during training. So the first term is just the regular cross-entropy loss in order to train a classifier, while the second and third terms control the calibration. So in particular, calibration requires a specification of 3 terms. So the first is what is called the in-layer specification, which talks about the regimes of data where your model needs to generalize to. And second, the regimes of outliers where the model must not generalize. And third, a suitable scoring function. So here, we adopt the popular energy-based scoring function directly from the vision community. And through this optimization, what we do is we calibrate the energy score such that it is consistently low for the inlayers and it is consistently high for the outliers. Thereby, we doctor this training. And once this training process is completed, so we just take the pre-trained model and utilize a standard energy score, as you can see on the left, to find out whether the test time data is in distribution or not. And this energy, as I've said, is a popular score, is essentially an exponentiated version of the logits of a classifier, and it is derived, it can be easily derived from the softmax distribution. So how we have actually done this in practice is we realized this inlier and outlier specification losses through the use of margin-based loss functions, where we enforce that the energy of the inlayers should be significantly lower than the threshold and vice versa for that of the outliers. How is this optimization actually done in practice? So one way to specify the inlayers would be to utilize a set of held out calibration data from the train set. But if you think about it, it becomes very challenging in limited data scenarios. In order to specify the outliers, a representative OD dataset can be used, and it is actually the best if one provides it for free. But it is very non-trivial and it's significantly challenging in order to obtain such a dataset, and especially crucial problems in medical imaging. And the third thing is, care must be taken in order to ensure that this calibration process does not compromise on the capability of your detector to generalize to the inlayers, that thereby preventing over-conservative models. So a way to address or combat these limitations is through the promising route of data augmentations. So one way to specify the inlayers would be to define augmentations in the pixel space. So typical examples include the geometric transforms that we are very familiar about. For example, the rotation, translation of images. Or one can even adopt standard toolbox-based augmentations, for example, augmix, pixmix, and so on, which are currently the state of the art. So in order to specify the outliers, though, Since we do not have access to a representative outlier data set during training in order to calibrate our model, so recent approaches in computer vision talk about synthesizing corrupted versions or severely damaged versions of your in-distribution data itself as synthetic outliers. And one such method is negative data augmentation, which does this corruption directly in the pixel space. And there has also been a recent approach that provides us a systematic way of how one can construct outliers in the latent space of the classifier, and that process is referred to as virtual outlier synthesis. So now we have the different protocols in order to perform the inlier specification and the outlier specification, and we have the energy scores for appropriately calibrating them. So now let's see how these benchmarks, which are very popular in the regular computer vision literature, are effective in case of detecting these open set data. For example, when we utilize augmix plus VOS, which is essentially pixel space inliers and latent space outliers, or augmix plus NDA, which is essentially pixel space inliers as well as pixel space outliers, they do not seem to perform well, and only in a few cases they even match even a simple baseline detector as that of the generalized Odin. And surprisingly, on a wide variety of experiments that we have conducted in this paper, we find that the OD detectors calibrated using the state-of-the-art calibration approaches do not perform well on modality shifts as well as novel class detection and when it comes to medical imaging. So there is a problem. Let's first think, what is the main benefit of doing this calibration? So let's assume a case where there is no outlier exposure or you don't do any type of calibration. The feature updates in a deep network are predominantly concentrated on isolated ID subspaces alone. And there are a lot of chances that your model could learn trivial shortcuts or biases in order to simply generalize the data. But once we introduce this calibration, the in-layer specification, as I was talking about, is used to expand the model generalization, and it identifies the optimal subspace for the ID data, thereby preventing and protecting against shortcuts and learning from trivial biases. But this process, in general, if it is it's unconstrained, as it just expands the regimes where the models can generalize. And this is where the outlier specification kicks in, and it ensures that the subspaces for the outlier data that we've actually defined does not overlap with that of the ID subspaces, thereby preventing overgeneralization. So this is the main point of calibrating all of these classifiers. But here in this paper, we make a very, very interesting hypothesis that how and where you actually do this calibration matters quite a lot in order for you to build well accurate OD detectors in medical imaging that do not compromise on your in-distribution accuracy. In other words, the space matters where you construct the inliers and outliers. And contrary to existing works, we, for the first time, advocate for the use of latent space for inlier specification and pixel space for outlier specification to perform this calibration. And this, we find it does not compromise on the in-distribution generalization as measured by the test accuracy. Our approach mainly consists of two main steps. So we first consider the training data. And now in order to construct what is called the latent space inliers, we take a set of training examples and extract the feature from the penultimate layers of the classifier. We then fit k class conditional Gaussian distributions with joint covariance. We then sample the low likelihood regions or the tails of each of the distributions. We call these tail samples as virtual inliers or hard inliers. Then we take those samples, which are of the same dimension as that of the latent space, pass it through the final prediction head, get the energy score, and then in our calibration, we ask it to significantly minimize the energy for these samples. But under the lens of the Gaussian discriminant analysis and the small analysis that we showed in our paper, we find that this pushes the energy of the tail samples close to that of the mean, thereby expanding the scope for generalization. But in order to prevent this overgeneralization and making sure that the model detects out-of-distribution data really well, this is the second step is the main contribution to it. So we synthesize high-severity compositional image manipulations through for augmix or rancon, and on top of it, we even corrupt the examples through a statistic destroying transformation, for example, zigzag, and we calibrate our model. So we take these pixel outliers, then pass it through the model, get the energy scores, and ask our model to produce significantly higher energy scores than that of your inliers. So we find that these diverse pixel space outliers ensures that the OOD subspace does not overlap with the ID subspace of the network. So in other words, we essentially draw a meaningful fence around this in-distribution data, which in turn helps us to generalize well and detect the OOD data well. So in our running example, so we see that when an OOD classifier is calibrated according to our proposed protocol, we find that the OOD rejection AURCs significantly improve. So we demonstrate the efficacy of our proposed calibration protocol along with the other baselines on a wide variety of open medical imaging benchmarks. So first, we evaluate our approach on a low-resolution 28 by 28 MNIST dataset, which contains images that are drawn from different imaging and acquisition modalities. We also experiment on high resolution, that is 224 over 224, ISIC 2019 skin lesions, as well as the colorectal cancer dataset. And for each case, we evaluate the OOD rejection performance over a wide range of data sets constituting modality shifts as well as the novel classes. We use the wide ResNet architecture for MedMNIST and the bigger ResNet architecture, ResNet 50 architecture for the higher resolution images. And in order to measure the performance, we utilize the balanced accuracy score as well as the AUROC OOD rejection scores. So to provide a quick visualization of the results in our paper, we provide this scatter plot here. So the x-axis here denotes the AUROC performance on the modality shifted data, while the y-axis constitutes the novel classes or those that share a lot of semantic similarity with that of the training examples, but those we want to reject it. So here, each of the markers denote a particular calibration protocol, and every marker, that is, if you take the star, for example, there are different, there are multiples of them. Each of them correspond to a particular data set that we have actually trained upon. So we can see that our proposed protocol consistently produces a very high OOD rejection AURC scores for both modality shifts as well as novel classes. We find that existing baselines, for example, those such as augmix plus NDA or augmix plus VOS, though in some cases produce good performance, they exhibit a large variance when we evaluate them over the benchmarks. And the table here also quantitatively compares our performance. Interestingly, we also find that our proposed approach leads to a well separation between the in-distribution as well as the out-of-distribution data in both novel class detection as well as modality shift detection, as you can see in the last histogram here, which shows the scores of separation. And this reveals the benefits of our calibration protocol. Interestingly, our approach can even detect nuanced covariate shifts that arise from different hospitals. So in terms of covariate shifts, the marginal distribution is going to change, but the conditional distribution, that is the label given the data, is going to remain the same. So here we have considered the Chameleon 17 Wiles data set, which consists of data drawn from 5 different hospitals, and we train our OOD detector and calibrate it with the data curated from 4 different hospitals, and we utilize the data from the 5th hospital as OOD. So we are able to find that while our method produces significantly high performance, the other baselines lack in detecting these covariate shifts. So as a summary, we are, and the key takeaway messages from this talk are, calibrating OOD detectors is significantly challenging when you consider the medical imaging use cases, and how and where we specify these augmentations play a very important role. And in particular, we advocate for the use of latent space inlayers and diverse pixel space outliers to drive this calibration. And we evaluate our performance on a wide variety of open set medical imaging benchmarks, as well as experiments on covariate shifts. So this is our project page, and you can scan the QR code if you're interested. Thank you so much.
Thanks for a nice talk. Time for questions.
Yeah, thank you very much for the, oh, can you hear me? Yep. Thank you very much for the nice talk. I was actually wondering, so when you showed these corrupted images, they look very, very, very corrupted. So it seems to me like the distance between your in-distribution and these corruptions is much larger than the distance between, for example, two classes in BloodMNIST or DermaMNIST. But it seems like your method still works really well. So for some reason, this separation does end up on the right side of the classes.
Right.
Can you shed some light on how this actually works then?
Okay. So first of all, these synthetic corruptions that we actually create is mainly used during the training stage. So that is used to mainly calibrate your OOD detector. And this essentially combats the overgeneralization property that your latent space inlayers would actually provide. So you can think about it like this. For example, when you sample from the latent space, you are essentially including the tail samples in your in-distribution. So the tail samples are kind of far away from the mean, and that is actually drawing a wider in-distribution, correct? But this process can actually go further and further, and you can, in fact, have a very big ball that you call as in-distribution. So when you synthesize this pixel space outliers, which are kind of drawn directly from the training data, you're actually curbing the process, making sure that your ID or the in-distribution is kind of well limited. So the main idea is you are actually learning how well and effective your in-distribution manifold actually needs to be, and there is a small fence around it. So the expectation is that this ID manifold is so powerful enough to characterize only the subtle variations that you can offer in your in-distribution, and it offers high levels of sensitivity when you include or test it on any other outlier data set. For example, the DermaMNIST, as you're pointing, that you were telling me, there is a data set that is kind of outside the support of your data. So we are able to find that this protocol essentially helps you to do that very well.
All right. It's surprising, but really cool that it works. So
thank you. Yeah.
More questions? Okay, I have one question before we leave. It's only very short. When we talk about calibration, what comes to my mind is the uncertainty estimations, right? So you want to have the uncertainty, the overconfidence. You want to measure that. While in this case, I think you are tackling more the open set recognition problem, right?
Right.
The open set recognition problem, right? So it's, I don't know if calibration is the proper word here, maybe. That's something that confused me a little bit.
No, thank you for this question. I see the point. But here, calibration, by what we generally mean is how you are essentially, telling the model how to work according to a given standard, correct? That's the general definition of calibration. So here, we want your model to work well on a separate set of data. We don't want the model to work well on a separate set of data, right? So that itself is kind of telling you the norm of how your model needs to behave, and that is why we call this entire procedure as calibration.
Thanks. So I think we are done. Maybe hold on. I don't know if IPEC wants to come. Someone else wants to come to say something.
We're not done. We have
Sorry for that.
teaser
Sorry
slides.
for that.
No worries. We are done with the oral session, however. Before we do the teaser slides, I do have an announcement that I will tell you after the teaser slides so that you stay and listen to all of them because they're all wonderful. Yes, but I really do have important dinner information that I will present to you at the end. So for right now, could I have all the teaser presenters for the short papers for tomorrow? Please come up to the far stage right. So, yeah. Okay, so our first presenter is S010.
Hi, I'm Christoph.
And the post I present is about an imaging modality called multispectral optoacoustic tomography. So it's a relatively new imaging modality which relies on sending short laser pulses into tissue and then recording the acoustic pressure waves generated by the so-called optoacoustic effect. And the key advantage of this imaging modality is that it enables imaging with optical contrast, but at acoustic resolution, so with imaging depths of several centimeters. And in the poster that I present, in the poster that I present, we introduce a deep learning-based image reconstruction framework for optoacoustic images that reconstructs high-quality images in real time so that it can be used during clinical diagnosis. And we do that by learning a well-posed reconstruction operator from synthesized real-world images. So if you want to know more, you find me tomorrow in the poster session this way. Thank you.
Thank you. We have S015.
Hello, my name is Adriana Dono Di Broto from ACFA Radiology Solutions. I'm here on behalf of my students, Matilda Bodriti, who cannot be here today. So I'm going to present our works about robust computation of cardiothoracic ratio from chest X-ray. So cardiothoracic ratio is actually one of the first measurements that you can do on a chest X-ray to see if the heart is of a normal size. What you normally do is you just draw two lines, one for the largest diameter of the heart and one for the largest diameter of the thorax, and you just compute the ratio between them. So it is a very straightforward measurement to be done on a typical chest X-ray, but the problem is, what if you want to compute it for a chest X-ray where the patient is slightly rotated, or if the lung is actually clipped away from the image? And then the second problem, what if you need to do this measurement very accurately and robustly for a large number of chest X-ray? So if you are curious about the answer, please come and visit my poster at W27 over there tomorrow morning. See you there. Thanks.
Thank you. And next we have S025.
Hello, everyone. Yeah, it's 26. My name is Nishant, and I'm from Carnegie Mellon University. I'll be presenting on temporal Monte Carlo dropout. So we have regular Monte Carlo dropout, which is sometimes computationally expensive because you have to run the model multiple times. So we figured that in situations where you have a stable probe or a stable scanner, in our case, we tested this on needle insertion videos for ultrasound. So in those cases, we found an algorithmic modification that can produce uncertainty maps that look pretty similar to the maps obtained with MC dropout. Again, there's a couple of things to verify. Because this is an algorithmic modification, we have to verify that the uncertainty maps are A, similar to the ones obtained with Monte Carlo dropout, and B, this doesn't affect the segmentation performances in any way. So we test both of these. If you're curious to know more, I'll be somewhere here tomorrow. Hope to see you all. Thank you.
And our next presenter is S036.
Hi, everyone. I'm Anna from the University of Bern. So in our work, we wanted to classify epithelial cells from H&E images. You can see here the major challenge that we faced is the high morphologic heterogeneity of the malignant cells. So this makes this task very difficult at the nuclei level. However, if you step back and look at the overall gland architecture, we can see that this is way more different from the normal glands to the malignant glands. So our idea here was to merge both a representation of the nuclei and the overall structure of the epithelial tissue, and for this we thought we could use a graph representation to make node classification and learn a new cell representation and accurate epithelial cell classification. So if you want to learn more, I will be poster 31 tomorrow morning. Thank you.
Our next poster is S059.
Hello, everybody. Probably many of you have heard about SAM, the segment anything model, which is trained on loads of natural images to segment them. we evaluated SAM on the Amos dataset and compared it to the state-of-the-art. And we found that it actually achieves promising generalization in these types of images. And we find, competitive accuracy with like effective point and box prompts. So if you want to know more, please visit us at the poster. Thank you.
Our next poster is S092.
Hi, everybody. My name is Saina, and I'm a PhD student at the University of Kentucky. In my poster, I described skin cancer as one of the most dangerous and sometimes deadliest kind of disease. Several fully convolutional neural networks had been suggested in order to aid medical diagnosis. Especially a symmetrical U-shaped structure has shown outstanding performance in this area. Since CNN doesn't have ability to capture long-range dependencies, we decided to develop and evaluate a transformer-based structure in order to capture both local and global representation. Please come and visit my poster tomorrow for further discussion. Thank you.
And S104.
Hi, I am Atik from University of Kentucky. So in this paper, we proposed a multi-stage forward contrastive pre-training strategy for improving the classification performance for medical image. And we found that our strategy got improved performance compared to regular backpropagation across different architecture choices and weight initialization. For more discussion, please visit our poster tomorrow, and thank you.
Okay, so important information. First, the dinner venue is the Parthenon, which is a one-to-one reconstruction of the famous Parthenon. This Parthenon was constructed in the late 1800s and is in Centennial Park, which is the large park adjacent to campus. It is within walking distance. Also, it is a famous monument. So if you use Google Maps or your favorite app to get there using GPS, it will find the correct Parthenon for you. Yes, it really is within walking distance, and it's a wonderful walk. However, there are also shuttles leaving from here regularly. It's not a large bus, but it's doing a small loop. So if it's not here, wait a few minutes, and it will come back and pick you up. Please bring your badge to dinner. Your meal ticket is in the back of it, and it is this foldable item. And if you have one that has an animal on it and you don't eat animals, see us at the registration desk and we can get you a different meal ticket. So yes, there's a short reception, dinner, music, and a group picture around 6:30, so you would want to be in that. We'll be on the steps of the Parthenon. I believe there's a short announcement from one of our admin about a picture here as well. We're taking a picture, that's the announcement. And the last thing, if somebody was looking for an EU to US plug converter, please see me at dinner, I will have one for you. So yeah. Otherwise, go out to the hallway where somebody will guide you, hopefully, to this picture. Yes, thank you. And see you at dinner otherwise. I have no idea. I was just told there's a picture. No. Okay. Sorry, the picture is actually in this room in this corner.
Right here. Over here.
They were quite coordinated.
Right here.
Thank you. Thank you, Terrence.
She can't see Tegan, she can't see you. rows. If you want to be in the rows, you just turn around. Come on. She can't see Tegan, she can't see you.
Good catch. Before you go, somebody left a hotel key. If you are missing a hotel key, I have it up here. It is gray and a key card. It is IHG. I don't actually know what that is, but yeah. If you are missing a hotel key, I have